Well, good afternoon. I'm glad you're all here for the last session of the meeting. And we're going to be starting in just a minute. And I just wanted to let you know a little bit about what we're going to hear in the next 10 papers. I found that we got quite a few very interesting and good papers. And it was actually a straightforward matter to create something interesting based on the quality. And basically what you see is that we have military, contractors, academia involved. In addition, we have some of our colleagues from Europe involved. And so it's going to be a pretty broad activity. And so I'd like to start with the first paper and get us going. We'll see how it all goes. Okay, the first speaker will be Michael Hart, and many of us know him. He's been in the field for years at the University of Arizona and Stewart Observatory, and he'll be producing a paper, Resolved Observations of Geosynchronous Satellites from the 6.5 meter MMT. And for the other authors, after about 15 minutes into the session, please come on up, and our colleague over here will set you up with a microphone so that you can give your talk also. Okay, thanks a lot. Let's hear from Mike.
All right, thank you, Glenn. Let's see if I can work out how this thing goes. All right. So this talk is something of a trip report on a one-night observing run that I made with Rich Rast from AFRL Directed Energy back in January of last year at the MMT, where we were trying to demonstrate what value that particular telescope with its adaptive optic system might have for SSA, particularly with respect to GEO satellites. Rich was visiting the University of Arizona on a 6-month visiting scientist appointment, which worked out very successfully, and we keep up that relationship and continue to work closely with him. Oh, that was the wrong button, wasn't it? Let's try that one. All right. So this is something we've been hearing about at some length throughout the conference here. Why SSA at GEO, but since it relates to a number of the things that we tried during our one night of telescope time, I wanted to run through this. Satellites in GEO, of course, have particular importance for both for civil, commercial, and military applications, as we know, for all of the reasons that you're all familiar with, communications and imagery of the Earth being particularly important. But because of their distance, at least largely because of their distance, those satellites are particularly vulnerable as well, in the sense that you don't call up your friendly local geomechanic and send him up there with a spanner when something goes wrong, at least not yet. Once they're up there, and when they break, they break. And then when they do, replacing one's extremely expensive, and it takes a long time to do it. So wouldn't you like a way of being able to monitor them for health and status, as well as their environments, to see if there's something potentially threatening in the vicinity, and to do that from the ground, because it's almost as challenging to do it from space as it is to put the satellite up there in the first place. Not that it can't be done. So why resolved imaging? There's all sorts of modalities that one can imagine, and people do, of course, as you know, for taking data on geosynchronous and geostationary satellites for purposes of health and status monitoring and threat detection. But various modalities suffer from various inabilities or inadequacies, resolved imaging among them. But it helps fill a niche that other modalities leave behind. Radar, for instance, it's the 1 over r to the 4th problem means that radar is extremely challenging to get that far, and the lateral resolution that you get is not very good because of the long wavelength at radio frequency. Optical telescopes can see GEO, at least at night, at least when it's not cloudy, at least when there are no big cities nearby, and so on and so forth. but to all ground-based telescopes, at least DoD telescopes today, they're nothing more than blobs of light from which you can tell some things. You can tell how bright the blob is as a function of time. You can tell where it is to very high accuracy. You can learn a lot from that. But there's a lot that is challenging, if not impossible, to learn from simply blobs of light in the focal plane of your large telescope, having to do with things like shape of the object, its configuration, its orientation, its capabilities, its dynamical behavior, its intent. Getting that from unresolved observations is hard, and maybe this is where resolved imaging has something to contribute. So when I say resolved imaging of geos with a big telescope, I don't mean a NIRS rating of 8, 9, or 10. I don't mean you look at it and you can see the rivet heads. This is resolved imaging with a few resolution elements along the satellite. Nonetheless, that's informative in ways that a simple blob of light is perhaps not. To get on with the trip report for the one night we had back in January of this year, we took images in near-infrared wavelengths with that telescope over there, the MMT on Mount Hopkins, southern Arizona, which has an adaptive optics system on it that we used in order to get rid of the atmospheric blurring effects that would otherwise render these satellites completely unresolved even from that big telescope. And this is a quite remarkable adaptive optics system. I have to put in a small plug for it because it's based on an adaptive secondary mirror that we built 15 years ago with support from Joe Janai, who I saw a little earlier. There he is. When he was director of AFOSR, he had the foresight to help us build the world's first adaptive secondary mirror there. And the darn thing keeps going. It's 15 years old, but it keeps plugging away better than ever and is able to produce diffraction-limited imaging, at least in the near-infrared wavelengths at this telescope, and gets more use. It's the second most used instrument on that telescope these days. It's quite remarkable, and we've pressed it into service for SSA here. The instrument we used, it's on the bottom of the telescope there. There's our instrument scientist, Don McCarthy. The Arizona infrared imager and a shell spectrograph. So it is an imager which takes images at these wavelengths, J, H, and K, astronomical bands, so 1.2, 1.6, and 2.2 micron center wavelengths. It also has a high-resolution shell spectrograph built into it. And we were hoping to get simultaneous imaging and spectra of these satellites, and weather factors prevented us from doing that, so we ended up just with the imaging part, but so we'll have to tackle the spectroscopy at some point in the future. And this will be resolved spectroscopy, that is spatially resolved spectroscopy, so we'll be able to look at things like the spectra of the bus separately from the panels. But that's for the future. Just to wrap up the sort of rundown of the specifications here, the field of view of the thing is selectable between 20 and 40 arc seconds. It's a 1,000 by 1,000 focal plane array, so the instantaneous field of view, the image, the pixel scale is 20 milliarc seconds or 40 milliarc seconds, which projects to a few meters at geo. And when you're running with the fine scale, you get the Nyquist sample of the diffraction limit, even at the shortest wavelength. So we took images, sort of bang, 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 once every 6 seconds, which is the readout time of the focal plane array. This is a rather old one, so it goes a bit slowly, but that's what we can do. An exposure time of 1 second, which is all you need to do to collect enough photons on a geo with a telescope that's that big. So this to get on with results. This is the first thing we tried doing, simply taking resolved pictures. So over on the top right there is a true color image of Anik F2, a Boeing 702 bus with 48 meters of solar panels, which happens very conveniently to sit right on the meridian if you're at the MMT. So it's gloriously placed to take images of this sort. There's a little cartoon off the Boeing website of what this thing looks like in reality, to scale with the image. So there's been no post-processing of the data there with the exception of flat fielding and background subtraction, whereupon we've added up the J, H, and K images as the respectively blue, green, and red color planes of this image. So let's say, so it's 64 seconds of total exposure per band, so that's a total wall clock time, start to finish, of about 18 minutes. 80% of it was thrown away because of our duty cycle, but that's because of the age of the focal plane array. About 6 resolution elements along the whole thing. Of course, that depends on the wavelength, so this is a rough number. And the thing you notice, of course, is that the solar panels look much redder than the bus. The bus is essentially white. It's uniformly reflective at all 3 of these wavelengths. Not true for the solar panels, which are invisible at the shortest wavebands we looked at. And we'll come back to that in a separate context in a couple of slides, why that is important from an SSA perspective. Something else we looked at is, well, okay, had there been a closely spaced object next to Anik F2, how small an object could we have seen, and how far away would it have to have been for us to see it? So these are contrast curves here for 2 exposure times, which were reflected. That's 120 seconds and 600 seconds here. This is the 120-second curve and the 600-second curve. And we took enough data to be able to, these are not extrapolations. This is based on that much data that we took. So on the vertical axis here is the minimum detectable size in centimeters going up to 1.5 meters versus the separation from the big bright satellite here, again in meters. So adaptive optics is important here. Of course, one can use other techniques like speckle imaging, as Gerard Van Bell talked about a couple of days ago in his images of a geo spacecraft from the Discovery Channel telescope, where he used clever post-processing techniques to produce something similar. Nonetheless, adaptive optics gives you a slight edge in that it puts the photons back where they belong in the focal plane, and thus avoids entrapping photon noise where it shouldn't be, which improves the contrast curves. So the bottom line is we could have seen a 20-centimeter object, assuming some canonical albedo, out to a spacing of about 100 meters or less with the data we had. So in just a few minutes, we can detect very small CSOs in the vicinity of one of the brightest geosats that's up there. So that was an interesting result. Photometry for all of this was done with a homegrown code that does astrometry and photometric calibrations. He's just an example of one of the data frames where a star conveniently zipped through the frame at 15 arcseconds per second. This code has several tens of millions of objects available to it in the visible and the infrared from well-known catalogs. It also has the ability to tell you whether or not you're going to be able to do in-frame photometry in advance of the fact by running the TLE through the catalog and saying, oh, nope, you're not going to find any stars, mate. You're going to have to go and do something different. But in this case, of course, we were okay, so we were able to do all the photometry that we needed from stars that were already in the data. And that produced things like this, light curves of a different, this is a dead rocket body. In fact, it's a Delta cryogenic second stage from a Delta IV launch up at GEO, and it's tumbling, as you can see, with a period of about 11 minutes, with a brightness in K-band, that's 2.2 microns, of averaging around 9th magnitude or so. This glint here coming off the curved surface lasts about 0.9 seconds. So there's a phasing issue between the length of the glint and our exposure time and the duty cycle. That means we didn't catch every single glint, but there's a very bright one. We caught 3.5 full rotations of this guy over 40 minutes. That's a bright object. Here's one that's not so bright. This is a much smaller satellite that averages about 13.5 magnitude in K, again observed with 1-second exposures, and that was part of the constraint that we were under at that time. And again, this focal plane array is 15 years old. So the limiting magnitude, which is probably up around 14 or so, or 14.5, is limited by pattern noise in the detector. With a newer detector, we'll do better. This drop in brightness of about a magnitude here, 5 minutes into the observation there, is real. We don't have ground truth data on what this satellite was doing at the time, but we know that the calibrator stars didn't show these same wiggles. They were constant. So all this behavior is actually real. See, one other thing I touched on earlier, the change in albedo of the solar panels as a function of wavelength. So these are images, again, of yet another geosatellite in the J band, 1.2 microns, H band at 1.6, and K band at 2.2. We expect these satellites to be unresolved, even at a 6.5 meter telescope, in these two wave bands. The bus itself is too small it's smaller than or comparable to lambda over d, so those are just still blobs of light. But in K band, we can see the panels beginning to appear, and these solar panels have a cutoff wavelength. You don't want them to accept infrared light because it doesn't produce electricity. All it makes is heat, and that's bad. So you throw it away, you reflect it away. So it turns out that on this particular observation, the solar panels are advertised in the open literature to be 12 meters long. Well, they're not. They're twice that long. They're 24 meters long. And this result is of some significance, but it turns out it requires a telescope of the size of the MMT in order to make it. If you ask, could you have done this with a 4-meter telescope, the answer is no, because you don't expect to be able to see these panels at wavelengths which could resolve them, because they're black at those wavelengths. But if you go to a wavelength that's long enough that you can see them, then you're defeated by lambda over d. The diffraction limit is too big. So you have to have a telescope that's of this size or bigger in order to have made that determination that the solar panels are as big as they are. So there is some unique value there in applying a big telescope to GeoSSA. So in that particular instance, yes, indeed, we need a bigger telescope. This is sort of getting towards the end here and wrapping things up. To resolve even a large geo object, we need a telescope of at least several meters in diameter. Adaptive optics helps in terms of putting the light where it's supposed to be, so we get to the diffraction limit with high contrast ratio. But then the number of resolution elements, n, is still low. So there's an expression here for it, which relates to the object length. Of course, the longer the object, the more resolution elements you can put on it. The bigger the telescope, the more resolution elements you get. And it's inversely proportional to the wavelength as well as the distance to the object, which for geo, of course, is pretty much fixed. So if I have an 8-meter telescope, I had a 6.5, but I can also get an 8-meter, then I find that I get 6 resolution elements across the thing, and now I can begin to see interesting features beyond just blobs of light. And we saw on the previous slide an example where that made a difference and allowed us to resolve or measure the size of the solar panels, and that's important in understanding capabilities of a satellite. If you know how big its panels are, you know how much electricity you can generate, and then you can begin to speculate or perhaps even infer what its abilities are. So just to conclude here, I would maintain that large telescopes equipped with adaptive optics have a distinct role to play in space situational awareness at GEO. That is, at the moment, completely untapped, and we can move forward with that. Resolved imagery allows us to see gross features and distinguish sizes. Whoops, high contrast. Let's try that back again. Darn it. Could you bring that one up again? I just want to make one more point before I wrap it up and Glenn hauls me off the stage. But
continue on.
So skip through to the end. Thank you. Large light gathering capacity helps. So the fact that the University of Arizona has large telescopes is well known. What's less well known, perhaps, is that we have a number of other key pieces of infrastructure that we're now bringing together into a facility, or an institute, if you will. We haven't quite decided what the name of it's going to be, for space situational awareness broadly, which will support research, education, as well as operational support to spacecraft owners. And there's a fairly large contingent of U of A people here who have talked to some of you over the last few days about that. But if anyone we haven't touched base with yet is interested to learn more, we'd be happy to tell you about it. Thank you very much.
Well, thank you very much, Mike. I do have we might have time for one or two questions, but I do have one that I thought was kind of interesting, because if you look at your 10-meter class telescope, 1 micron wavelength, look at GEO, we're roughly at 4 meters resolution, right? And you indicated that if you use some of your closely spaced object algorithms or whatever, you'd be You could see something on the order of 20 centimeters. And that's a small fraction of lambda over d. And I just wondered if you assessed whether or not you have the signal to noise to do that when you look at a geo object.
Yeah, that's of course, it's going to be photon noise limited, so it's going to go like the square root of the integration time, or the signal to noise ratio is going to do that. At those wavelengths where we will be, I did work this out and I honestly don't remember, so I apologize what the time was, where we get to be photon noise limited from the object rather than the sky background. But of course, you're right, most of the pixel, it's going to be one resolution element, is going to be sky, not object. But yes, if you expose long enough, you'll see a 20 centimeter object.
Okay, are there any other questions? It looks like we have one there. Okay, Rich.
Thanks. Mike, how much mount time is actually available for SSA on the MMT telescope?
Let's talk.
Okay, thank you.
Okay. I think we'll move on to our next paper. Thank you very much. And we have the first of our international guests, Giovanni Marco Dei. He's from the Italian Air Force, as you can see, and he'll be discussing Italian Air Force radar and optical sensor experiments for the detection of space objects in LEO orbit.
Thank you, sir, for introducing me. I'm Capitan Del Genio from Giovanni Marco from the Italian Air Force, and I started last year to work with the Aerospace System Engineering Group of the Italian Air Force, and I also was involved in the SST program. So today I would like to present the paper content and also to give you an overview of the Italian Air Force contribution to the implementation of an SST sensor architecture for space surveillance and tracking. This is the overview of my presentation, so we start with a small introduction. Then I will present to you some sensors that are parts of this national architecture, and also the experiment that we carried out in these last years. I will show you a monostatic radar, a bistatic radar, and an optical telescope. Finally, I will focus on the sensor integration activity and data fusion test, and at the end I will take some conclusion. So the Italian government recognized the relevance of having a space surveillance tracking sensor architecture some years ago, and in order to protect its own space and satellite system from against the damage or destruction from collision with other space debris. In 2011, the Italian government dedicated the Italian Air Force to make a feasibility study with other organizations, such as the Italian Space Agency and the National Institute for Astrophysics, in order to try to build up a sensor architecture using only existing sensor already installed in the national territory. So after that, Italian Air Force started a survey at the national level and carried out some of the experiments that I will show you today. In 2014, the European Commission established a European SST consortium in order to integrate all the sensor and processing system available from European nation in order to create an SST, European SST surveillance network. So now this consortium is composed of 5 nations, and Italy is one of them. Our national sensor architecture is composed of ground-based sensor, and we have a heterogeneous sensor, radar, optical telescope, and laser. Laser will be out of the scope of this presentation. And also, this sensor, we know a heterogeneous sensor can give the possibility to have different type and different type of capability, operational condition, and also a complementary type of information. Also, the observation mode is to take into account because these sensors are able to make survey tasks and tracking tasks. The survey when the position of the object is not known a priori, and while the tracking when we already know the object, but we would like to follow it and to get high accurate data. And in this picture, you can see the sensor that I will present to you now. We start with the monostatic radar. Then we will see a bistatic configuration radar composed of one transmitter and one receiver. And finally, the optical telescope. So the first radar is the RAT-31DL, also known as a FADR, Fixed Air Defense Radar. It's a D-band long-range radar developed by CELEX-ES. Italian Air Force employs currently 14 of these radars, and 2 of them are also deployable. It can transmit multiple independently phase-controlled pencil beam in order to track simultaneously different several targets, such as air, missile, and also tactical ballistic missile. This radar was selected for the SST experiment because of the 2 particular capabilities. In fact, it can direct high elevation beam pointing when it is used in TBM tracking mode, and also because it can be externally cued against an existing track. As I said before, this radar was not designed for ST, so we knew that we had some limitation in the test, in particular due to the target altitude and velocity that are not comparable with the air missile target. We choose one of the Italian Force the Italian Force radar that was located in Borgo Sabotino Air Force Base, and it was optimized for SST in the timing, waveform, and processing feature, making some small modification in its software, in the software performed by CELEX-ES with no cost. One of these modifications allows the radar to process target beyond the instrumental range. In fact, echoes from target coming from that were located in the biggest zone were also processed in the second time frame. So for the test, for the experiment, we select a subset of a spare object from the NORAD catalog, and we use the TLE data for queuing the radar. Here there is a summary of the result of this experiment. We know we didn't expect any excellent result, but because the objective of this test was just to demonstrate an initial space sensing capability. In fact, the radar was able to detect debris with a radar cross-section greater than 15 square meters. That is a quite big number, at a distance of 1,000 kilometers. As you can see from the picture here, we observed a good matching between the TLE trajectory and the raw data coming from the radar, so the radar plot. We observe also some slight bias error when the radar try to detect smaller targets. Overall, so we can say that it has a good SST performances, consistent with its power aperture limitations. After that test, Italian Air Force asked the CELEX-ES to make some hardware upgrades on this radar in order to improve the characteristic and to have for example, to increase the power in order to increase also the range. The second sensor that I would like to present to you is the Barales radar. It's a bistatic radar composed of 2 antennas. The flight termination system, that is the transmitter, owned by the Italian Air Force and located in Sardinia. It was usually used for safety purpose in the live test range in Sardinia. But here the main sensor is the receiver. That is a very big antenna, the Northern Cross antenna, operated by the National Institute for Astrophysics. In fact, it was used for astronomy purposes. It is a transit instrument that is steerable in declination, so it can detect objects that transit over the local celestial meridian. It is a very big antenna composed of two long arms, the east-west arm and the north-south arm, that are composed of a great number of reflector and parabolic antenna. With this sensor, we expect to detect orbiting object of very small radar cross-section, in addition to very important capabilities that are the multi-beaming that enables the characterization of the trajectory of the orbit object, and also it can provide ranging data when it is coupled with the transmitter that can use synchronized and modulated signal. We performed two observation campaigns in the past. The team that carried out this experiment was composed of personnel from Italian Air Force, Italian Space Agency, and the National Institute for Astrophysics. In the first experiment, the objective was to verify the sensitivity of the system and also to determine the minimum radar cross-section detected by just only a section of the east-west arm. On the right, you will see the results. So at the end, the system was able to detect sub-meter object with a distance from Earth until an altitude between 300 and 1,000 kilometers. Also for object, it was also able to detect object greater than 1 square meters until an altitude of 1,700 kilometers. In the second experiment, the objective was just to test the multi-beam capability, and we used only a section of the north-south arm, in this case, called BEST2. And at the end, the system was able to recover a pattern from the multi-beam picture, and after a post-processing algorithm, was able also to reconstruct the trajectory of the orbit object. Here there are some outcomes of this experiment. On the right-hand side, on the left-hand side, we can see a time frequency graph when you can see here a detection of a very small debris with the radar cross-section equal to 0.5 square meter. In the middle, there is the multi-beam picture that we test in the second experiment. You can recognize the pattern here that thanks to that it was possible from that pattern to reconstruct the trajectory of the orbiting object in terms of right ascension and declination. Okay, now the last sensor, but not the least. It's a PDM MIT telescope that stands for Pratica di Mare, that is their first base, where it is located. MIT military telescope, so it's an optical telescope that Italian Air Force acquired some 2 months ago, and it was designed for SST and developed by 2 Italian companies, GM Spazio and Officina Stellare. Here you can see some of its features, so the coverage 306 degree by 90 degree in azimuth elevation with a diameter of 350 millimeters, and a focal ratio of 2.8. So it is equipped with 2 coaxial CCD sensor, one with a wide field of view that it's used for survey tasks, while another one with a narrow field of view for tracking with a greater resolution. It is mounted on a platform in equatorial layout, so it's designed also for high-speed pointing. This sensor can be used, as I said, as a survey. So when the sensor can scan a portion of the sky, as default, it can use two types of movements, the spiral movements or linear movements. Otherwise, the operator is also, can also set some waypoint in order to define a specific search path. It can also be used for tracking, so we will try to follow an object, but it requires naturally to be queued by an ephemeris file. Now I want to show you the procedure that we are following in this month in order to make the image processing and the orbit determination process. The images acquired are analyzed and then processed. And first of all, there is an automatic star matching process using a star database, and then a time synchronization using a GPS sensor. After that, we take the tracklet here, and we take the first pixel and the last pixel in order to extract the right ascension and declination for each point. We will collect this data in a GISC file, and we repeat this process on each image. After we collect all the data, we will ingest this GISC file in the orbit determination toolkit in order to make the orbit determination. It's fair to say that tests for verifying sensor performance are still in progress since we acquired this telescope 2 months ago, and we are focused on LEO satellite of European interest. Here there is a small list of satellites that we are tracking in this period. In particular, I would like to focus to Envisat, that is an ESA non-operational LEO satellite. We choose that in order to perform a campaign over 3 days, an observation campaign over 3 days, in particular because it has a stable orbit, because we don't have any maneuver so far because it's not operational. So you can see here 10 detection of this satellite taken in one night. We collect all the data of this observation campaign that lasts 3 days, and at the end we collect an overall amount of 50 detection. We analyze this data, and we saw that the position uncertainty improves due to the increase of the available data. So we can see, here the analysis made just using the data from the first day. They here using the data from first and second day, and then all the data collected in the campaign. For example, the radial position uncertainty evolves from a maximum of 150 meters to a maximum of 60 meters. And the sensor gave its best performance in the cross-track component of the position uncertainty. That was maximum value the maximum value was around 37 meters. Okay, now the next step will be to try to integrate all these sensors. Here you can see where they are located, so they are quite geographically dispersed. We will soon establish the Space Operational Center in Pratica di Mare Air Force Base, where the telescope is already installed and controlled by control room. In this Space Operational Center will be operated by Aerospace System Engineering Group with the collaboration of other organizations like the Italian Space Agency and also the National Institute for Astrophysics. What is next? So we would like to perform a data fusion test when we will integrate all these sensors in order to determine the potential benefit in orbital estimation of using multiple heterogeneous geographically dispersed sensors. Here there is a list of the objectives that we would like to obtain with this test. In particular, we would like to focus to the first one. So we would like to try to add the ranging data coming from the FAD radar to the angle measurements obtained by the PDM military telescope. We already run some simulation. We create a valid environment of simulation using some simulation tools like STK or DTK for the determination, and also spaceflight simulation. We run some simulation. We already observed that adding the ranging data to the, for example, to the measurements made by the telescope on the Envisat LEO, Envisat satellite, we observe that the accuracy improves, so the position uncertainty decreases again. So now I would like to conclude my presentation. I'll show you some of the sensors that are part of the national architecture. in particular those that were tested by Italian Air Force. Those tests demonstrate that our sensors are compliant with the requirement defined by the European SST consortium. So we are confident to say that Italy can give an important contribution in producing an integrated European for space and surveillance network. Thank you for your attention. Here you find my contact information, and I'm available to answer to some questions. Thanks.
Are there any questions? Okay, we'll move on to the next talk. Thank you very much.
Thank you.
Okay, the next talk will be given by Michael Werth. He's a system engineer and imaging scientist at Boeing, and his talk is entitled Incorporating LWIR Data into Multi-Frame Blind Deconvolution of Visible Imagery. And so let's see how Michael intends to exploit the infrared.
Thank you. Good afternoon. Thank you very much for having me. Yes, I work for Boeing. I work for Boeing here in Maui. I work with the Haleakala telescopes, the 1.6 and the 3.6 primarily. Can I get a quick show of hands? Who here is not technically inclined? I want to see managers. I see Jerry over there. You're not technically inclined, buddy. Anyway, I want to try to encourage our non-engineering friends to stay. I'm going to show some very pretty pictures, and I hope that you're impressed by them. But we first have to get through a tiny bit of math and technical detail. So why don't we go on to the next slide? How does this work? Oh, it's the big green button. Great. So how do we recover images? Essentially, we use multi-frame blind deconvolution. It's a family of speckle imaging techniques that take the image on the left. This is raw image. And maybe we use adaptive optics to sort of improve it, and usually that works pretty well. But really, we want something that looks like this on the right. And this is what you can get by combining adaptive optics with software reconstruction. So speckle imaging just refers to a whole family of techniques for removing atmospheric blur from an ensemble of images. So how does it work? Well, we make a few assumptions. Sometimes they include that things are temporally invariant. You don't want your satellite to be tumbling particularly fast or rotating very quickly. So in a set of frames, you are assuming that it's relatively stationary. And if you're integrating short enough, that's usually true. And we also tend to assume a finite object support. So this is actually a mathematical term for our non-technically inclined friends. Basically, it just means that you can enclose the object in some sort of circle or other shape. It's basically, you have a satellite and it's against some sort of background. That would be a good way of phrasing that. So what do we tend to see? We tend to have some sort of object that we're reconstructing. The turbulence causes blurring and might wind up with something that looks like this. And then we add noise on top of that, and this is called the linear forward model. But that's not really that important for this talk. All you need to know is that we're using an iterative method to simultaneously estimate the PSF and the object, and there's a lot of details that go in behind that. People have spent entire careers on this field. We're going to ignore most of that today. There are a lot of problems here. Here's another math term. MFBD is an ill-posed inverse problem. You can take that as meaning that it's very hard. We need to suppress the amplification of noise. You just have a bunch of garbage and you're trying to construct something pretty out of it. It also tends to be computationally intense. You might have like a supercomputer that you dedicate just to doing MFBD problems. There are a number of ways to improve things, though. There's actually a poster in the area next door on iterative reweighting, and Brandon Califf gave a talk on that last year as well. There's also some things like phase diversity, wavelength diversity, and various other ideas for improving things. But today I'd like to talk a little bit about wavelength diversity, and you can probably guess what that means. It means using diverse wavelengths, more than one. So the central thesis here is that the atmospheric blurring function tends to fall off with wavelengths. So here's a really good two really good examples. So here, simultaneously, we recorded data on a star in the visible, sort of I-bandish and LWIR, which is much longer wavelength. And you can see, just through the atmosphere, this should be a dot. I mean, it's a star, it's a point source. But you get a lot of blurring in the visible and not nearly as much in the LWIR. And a better example is actually these Hubble images over here. You can't really tell what's going on in this image. It's just a big blur of nonsense. But over here, you can actually kind of make things out. This is clearly a telescope, maybe with some solar panels. It's rather interesting that you're able to resolve additional images at a longer wavelength, even though the inverse might have been true if you had no atmosphere at all. So we came up with a question of whether we could maybe use LWIR in some way to improve our visible MFBD processing. And one thing you could try to do is estimate this object support region. So the object support is actually really difficult to estimate from raw data. And you can see, here's a really good example of this. We have this really fuzzy, short exposure image of HST, and you're trying to estimate what the final object looks like. So if you had a perfect, pristine example of the object, you could just perfectly draw a little line around it, and you would say, this is the support region. But we don't have that. We have a bunch of blurry images, and they're probably bouncing around. So here's what we get if we just try to do something relatively conservative, because we don't want to accidentally cut it off. But this is really much larger than the final reconstruction. You can see there's all of this background that got included in this recovery. And that's maybe suboptimal. I mean, we're wasting a lot of additional resources. Those pixels are part of the minimization, so that's a lot of computation power that sort of went to waste. You're also kind of degrading your resolution when you do this, because initially you assume that you have a really tightly bound constraint if you can. So we want to try to use LWIR to maybe estimate the constraints, since if we can get the support from LWIR, which we know is relatively good, then maybe we can improve our visible image processing. So here's what we do. We take some LWIR images that are recorded at the same time as our visible images. We just rotate them, zoom in on them, make sure everything's nice and centered. And then we do some sort of thresholding. I chose Otsu's binarization, but there's a lot of really nice thresholding schemes that you could apply here. And that gives us a new support. And you can see that this is a fair bit smaller than our visible support. So maybe this is going to be able to give us a better answer, or at least an answer in less time. And here's an example of what we did. So we took some uncompensated data of GLAST, which is also known as Fermi. It was renamed at a later point. So if you know it by Fermi, this is Fermi. It's a gamma ray telescope. Oh, can I go back? Yes. Oh, beautiful. It's maybe a little difficult to perceive, but there's this fuzziness that got reconstructed here, and it seems like that's kind of gone in this image, and maybe the dynamic range has changed a little bit as well. So we didn't do anything different with these images except for apply this LWIR object support estimation method, and it kind of looks noticeably better. So here you can actually see the support being generated for each reconstructed frame versus the visible support. And look at all this extra background that was actually taken out by using the LWIR data. And yeah, it's not a perfect reconstruction. I mean, the LWIR is a longer wavelength, so there's less resolution there intrinsically. But I think this is proof positive that this idea could work. So if we look a little more closely, you can see that here's the LWIR support in gray. It's taking up much less area than the visible support, and so that's good. So these reconstructions were created in about 20% less time, and they had about 20% better resolution using a resolution measuring method that we call the MMLSF, and it was an AMOS paper, I think 2 years ago, if you want to go look that up. So this is great. I mean, this is exactly what we thought might happen, but maybe we should continue looking at other examples. And here's another slide where we just kind of point out, yeah, there was some fuzziness here, and then the fuzziness was gone. Yay! What if we use AO compensation, though? You might guess that with AO compensated data, your support estimation is relatively straightforward to perform, right? It's not nearly as blurry. The residual PSF that's left over is probably pretty small. And that's exactly what we're seeing here. So, it's actually pretty tight on what the overall object looks like. There's maybe a small reduction in overall area, but the original AO compensated data actually looked pretty good. So then if we actually analyze things, we got a marginal improvement in processing time and also a marginal improvement in resolution. Maybe the area of this is slightly smaller. Nothing really amazing, but you don't always necessarily have an AO system. They can be expensive to use and implement, and so this is an interesting conclusion. You might have thought, maybe this method would just work all the time, but yeah, this actually does make some sense. And here's an even neater example of HST. If you pay attention on the right, when we use the LWIR support, sometimes you see little features getting cut off. So like right there and down here, and there's also this antenna on the right side, which is conspicuously absent over here. And if we look at the same animation with the support, you can see it's kind of absurdly tight. So this is an aberration. It seemed like the LWIR images in this specific case were just really narrow, and we don't really have a good understanding of why. So maybe the technique needs a little more refinement, but overall we did find some interesting results. I think this was a very neat case to point out and discuss. And you can see that here's one sample image. The visible support was enormous, so this is, the PSF was pretty bad this day, so you wound up with, a support region that was almost the entire frame. But then we wound up cutting it off a little too much with the LWIR, so we were a little aggressive, I guess. We could probably solve this by just maybe eroding the support region a little bit and, trying some other tricks, maybe anti-alias this whole thing. But there's a number of ideas we have for maybe improving this technique. So in conclusion, we do have a paper on the AMOS Tech website, and we measured about up to a 40% improvement in processing time. Sometimes it was actually really stark how much benefit you could get out of this method. And other times there were examples when, if you're using AO, it tends to not perform so well. Can clip object features that don't appear in LWIR, so that's another problem that you have to consider. If your object has some really hot and really cold features, like some sort of large temperature gradient, you could assume that maybe this wouldn't work as well because you'd be creating an object support based on missing information. We could probably anti-alias the support estimate. I don't know how much benefit that would provide, but it's something that we should try. And we need to really investigate this image clipping issue. Maybe also iteratively try to create new supports as we work down on the reconstruction. But that's the end of my talk, so are there any questions?
Okay, well, the next paper will be given by Stephen Griffin from the Boeing Company. And Steve has more than 25 years experience in structures and vibration management, and he's applied it in both applied and basic research. And he'll be telling you about his new aperture partitioning element. Okay, Stephen.
Hi. First, I'd like to give thanks to Brandock, who's also in the audience, and Stacy Williams, my co-authors. And let me figure this out. All right. So I'm going to be talking about, first of all, a little bit by way of motivation, the benefits of aperture partitioning. That's not my specialty at all. I'm more of a mechanical person, so I'm going to mostly be talking about the device we put together to accomplish aperture partitioning and the various challenges in doing that and where we are now. I'm also going to be talking about where you might put an aperture partitioning element in the optical path and where we ended up putting ours. I'll give a hardware description, talk a little bit about the design and analysis involved. And we've actually built this. It's working. It's integrated into the telescope, so I can show you some wavefront results and some preliminary image results, and then I'll draw some conclusions and also talk about where we're going with this, so what we plan to do next in this area. So Brandok's Caleb's in the audience. This is really his slide. So if you accept for a minute that given an atmosphere and given a large telescope that there's benefits in post-processing in chopping the image up into several images, then you can, the next question you might ask is how would you do that? And there's several ways to do that in the literature. The way we've selected is to actually use a partitioning element. So in this case, we're looking at the partitioning element we built divides our image into 4 images, and it's placed at a telescope pupil. And the results shown are synthesized, and really, if you have questions on this would probably better be directed to Brandok. But let's accept for a minute that this is a good idea and talk about how to actually get to this point. So you could do this at any pupil. You could use a telescope with a segmented primary mirror, and you could use that to come up with a partitioned element set if you'd like to. Where we placed our aperture partitioning element is down in the first floor of the facility at a pupil that we made especially for it. And our element breaks the image up into multiple images and onto our camera. We considered both reflective and refractive, and we selected a reflective element to avoid dispersion and also just as a way of not losing any light in our images. So here it is. This is notionally the idea. You have 4 annular segments at the top, and when Brandok first came up with this idea, I want to split up the picture into 4 pictures. The initial idea was, well, let's make a fixed optic. So if you can imagine a wedding cake with sort of canted layers that move the images into 4 different places on the image plane. That was the initial idea. And that sounds like a really hard optic to make, and it was. We had a design, we put it out to vendors. No one was interested in bidding on that. That was too hard to make, it was too hard to polish. I think we got 1 bid back, and they relaxed our requirements to the point where it wasn't even going to be a useful optic. And this is the point where I got involved. So Brandok walked into my office and said, why can't we just take 4 separate segments and just move them? So that sounds like a pretty easy idea. And I said, well, shoot, I've built a lot more complicated optics than that. So that sounded like a pretty easy thing to do from my perspective. So that's the course we ended up taking. So once you say you're going to have 4 annular segments, and that becomes a lot easier to build. So a lot of people are willing to build you 4 annular segments and polish them. Then the trick is how do you move them around? So that's mostly what I'm going to be talking about. The segments we selected are diamond-turned aluminum with a silver coating. Aluminum's helpful because we ultimately want to tap into the back of these and attach to them, so that was a good material to select. We were considering 2 different configurations. The device we ended up with can do both of these, either 4 in a row or 2 on the top and 2 on the bottom. So when you think about this device, you can do a Zmax simulation. You can, given your camera and your focal lengths and all those factors, you can figure out what your maximum excursion needs to be on each annular segment. That's a very exaggerated picture up top just to illustrate what's going on the segments. But you need to tilt the segments. And it turns out that the maximum angle we needed to get to move our images around was 1 degree. And that helps you understand the gaps between the segments. So you don't get to keep all the light. You lose a little bit in the gaps. And we also came up, based on the kinematics, with an accuracy requirement. And the point of that is someone's going to have to actually move these segments around to a point on the image plane. They're going to have to be able to do that in a reliable way. And once they get them to that point, you'd like them to stay there. So there's basically a minimum, some minimum resolution accuracy that you'd like, so that when you turn the knob, it doesn't go too far, and you're able to reliably move it to a position. So that number I translated directly into the positioner requirement of about 4 mils or 4 milliinches. So looking at various, also we didn't really want to make this an active, at this point, an active element. We wanted it to be able to just put it into a location and have it stay there. So we were looking at two different actuators. We considered two. One is just a threaded adjuster, and if you look at the threaded adjuster there on the left, believe it or not, the gray part that you can see there, let me see if I can figure this out, this part, these are threads. So you can't even see the threads on this with your eyes. It's 254 threads per inch. That cost about $20 for a threaded adjuster that's 254 threads per inch. And of course, one turn of a 254 thread per inch screw is about 4 mils. So anybody can manage to keep track of one turn at a time on a threaded adjuster. So that meets our resolution requirement pretty handily. So that seemed like a good choice. Another good choice that would keep someone from having to get in there with an Allen wrench is this idea of a squiggle motor. I don't know if people are familiar with that, but that's a relatively new technology. It's very exciting. There's this black part is a kind of a hollow casing that encases a screw, and there's piezoceramics on either side of the black part. And you basically have a degenerate resonance that you drive, and if you get the phasing right, the screw moves in and out. So it's a fixed, once you get it where you want it, it stays. It's got a tremendous range, and it's got a good resolution there, much better resolution than the threaded adjuster. We decided not to go with it for this project just because we figured we didn't want to have all the extra baggage of the amplifier and the controller in that part. So once we decided on the threaded adjuster, the only part, the tricky part left was, as you saw, the threaded adjuster has a ball end. So if you put the optics on the threaded adjuster and you turn it sideways, of course the optics would fall off. So you need a way to hold the optics onto the threaded adjuster. And as you move the 3-point mount of each of the optics, you want to be very careful not to exert a moment onto the optics, because that would give you some wavefront distortion. So I came up with this idea of using these electroformed bellows flexures. So these are very common. They're very inexpensive as well. And so the bellows flexures have a known compliance in the direction of motion of the threaded adjuster, and then they have hardly any stiffness in the moment direction. So that allows you to apply a preload, basically hold the optic onto the ball, and then keep from exerting a moment as you achieve your angles. So that was the idea. I had to do a little bit of analysis to prove that before we actually built the device. So I did just actually only 2 pieces of analysis. They were both finite element analyses, and one was kind of a conservative idea. If I just supported an optic on the just the bellows, how much stress would I get in the mirrors? I figured if that was a small number, then I probably didn't need to worry about gravity sag, and indeed it was a very small number. 0.01 psi is not enough to worry about in terms of a wavefront distortion in this optic. And then I also did an enforced angle of the maximum tilt, which is 1 degree, and looked at the distortion, and again, the stress was negligible. So this told me that should I build this device, I shouldn't have to worry when I reposition the optics that I would pick up more wavefront aberration. So we had the device built by someone in Albuquerque. The company was Megcor. I've done a lot of work with them over the years. They put the device together, had no problem procuring the flat optics, the flat annular optics. And when we measured the wavefront of the individual optics, they met our requirements. Some of them were better than others. They were all on the order of about a 10th wave. I think one was about a quarter wave. It would have been nicer if those numbers were smaller, but they did meet our requirements for static aberration. More importantly, when we moved the optic around, we did lots of tests where we moved it around. We didn't pick up any additional aberration, and the shapes, the wavefront aberration stayed the same. So we were really happy with that. This is the actual device in place. So you can see, I think, yeah, this shows. So we have it on a stage so we can switch between the full aperture and the partitioned aperture. And you're just seeing the front of the device there, and each of those segments is at a little bit of an angle. Here's some preliminary results. We haven't had a lot of time on the sky with this device yet, but here's some preliminary results where we're able to resolve a binary. I don't believe we have an equivalent result without the aperture partitioning element, but that's the eventual goal, basically, to show that we get an improvement with the aperture partitioning element. And then there's also the HST over there with the aperture partitioning element. So my last slide is where we're basically, it works. It's in place and it's working. We expect to get a lot more time in the future with this on Sky. Some future improvements that we're exploring, we got a small AFOSR grant to look at an active device. I'm really excited about this. The active device, what we'd like to be able to do is keep the idea of aperture partitioning, but then be able to instantaneously phase segments. So what that would allow you to do is you could go from 4 segments to 3 segments to 2 segments to 1 segment, depending on the signal and noise ratio in your pass. So that's a considerably more complicated device, but I still think it's a relatively simple device to build, and that's what we'll be working on in the next year. That's all I have. Thanks.
Well, thank you very much. Are there any questions?
Thanks
Okay.
again.
Okay, thanks a lot. Okay, our next paper will be presented by Celine Dorgeville. She's an instrument scientist, basically laser physics at the Australian National University Research School of Astronomy and Astrophysics. Her paper is entitled From Dye Laser Factory to Portable Semiconductor Laser, 4 Generations of Sodium Guide Star Lasers for Adaptive Optics in Astronomy and Space Situational Awareness.
Thank you for the introduction.
I hope I got your name under control.
Yes, you did. All right, good afternoon, everybody. It's my great pleasure to be here today. I've longed to come to this conference for a number of years. I used to work next door at the Big Island at the Gemini Observatory, where I worked as a laser scientist, laser engineer to put a sodium laser guide star on the Gemini North Telescope in Hawaii and the Gemini South Telescope in Chile, where I worked next. And I'm now with the Austrian National University. So all my background is in sodium laser guide stars. I've been involved in this field for 15 years. And been working for astronomy initially, but also now for the space situational awareness community, as we're involved with the Space Environment Management Research Center in Canberra in Australia. How does this work? Okay, so this is the outline of my presentation. I want to talk about sodium laser technology. I want to review what's been done in the past and also explain why we want to propose another approach. So you probably already know, if you've been involved with adaptive optics, that the principles were proposed first in 1953 by Horace Babcock, and it was in 1985 that Foy and Laberry proposed the idea of using artificial stars created with lasers in the case when the science object wasn't bright enough to do adaptive optics on it. So there are 2 types of laser guide stars, the relay guide stars and the sodium guide stars, and I'm only going to talk about the sodium guide stars in this presentation. So there's a little background about the laser-sodium interaction physics that you would need to know to understand why you go for certain laser formats and not others. You want to maximize the number of photons that you get from the sodium layer. And there's a few key points you need to remember. First, you want to use circular polarization because that produces more photons coming back towards the ground. And you want to use not only the sodium line D2A, which is the strongest line where most of your laser power is going to be locked, but you also want to have a little bit of power on the sodium D2B line, and it's called D2B repumping. There's another thing that's important is to understand that the sodium photon return is going to change depending on where you point your laser, and that's because the Earth magnetic field has an impact on the strength of the interaction. So not very long after Foy and Laberry proposed the idea of using laser guide stars, Thomson and Garner went ahead and used a sodium LiDAR to create the first sodium laser guide star on Mauna Kea in '87. Around the same time, work was being done at the Starfire Optical Range to develop laser guide star adaptive optics as well, using Rayleigh lasers, and so it didn't make much sense after astronomers starting in that game to keep everything classified. So that work was eventually declassified, and civilians and military adaptive optics scientists could exchange information and progress the field. There were a number of demonstration lasers in these early days by the University of Chicago, for instance, at Yerkes Observatory and the Multimirror Telescope in Arizona, using continuous wave dye laser, very low power, about 1 watt. And then the Lawrence Livermore National Laboratory thought, well, that would be a good idea to actually use our AVLIS laser, you know, the one used for isotopic separation of uranium with lasers, and pointed to the sky and see what happened. So they just used their 1 kilowatt laser and did just that and created the brightest sodium laser guide star ever created. It is said that they could see it with the naked eye. So they demonstrated they could do that, and so they went ahead and created a facility laser system for the Lick Observatory based on that same pulsed dye laser technology that AVLIS was using. And a second generation of that system was developed for the Keck Observatory, which started operation in 2001 and has been in operation since then, delivering really good laser guide star adaptive optics science for astronomy. Meanwhile, in Europe, people decided to use continuous wave dye lasers. At the Calar Alto Observatory in Spain, the first facility system was installed by Max Planck Institute. They went ahead and developed a second generation system for the European Southern Observatory, very large telescope in Chile, which was called Parsec, and saw first light in 2006, the first laser guide star created in Chile. Meanwhile, solid state technologies were maturing, and in '91, Tom Jays developed a micropulse some frequency laser at the MIT Lincoln Lab. And that system was the grandfather of a number of systems which I'm going to describe now. The University of Chicago got a second generation of that system, which they further developed, and eventually they demonstrated on the sky a number of times, and were able to install at the Palomar Observatory Hale telescope, the 5-meter telescope there, to be used for science for 5 years. The Starfire Optical Range, after doing experiments in Rayleigh guide stars, adaptive optics, also started a development program for sodium laser guide stars. They settled on a similar technologies, however, using continuous wave single frequency lasers, which actually was a very good idea because it turned out to be the most efficient system to excite sodium atoms. They created several versions of that system, 20 watt and a 50 watt version, and in a very landmark experiment, they combined those two beams on the sky. One was tuned to the sodium D2A line, and the other was tuned to the sodium D2B line, and they proved that you can get a significant photon return enhancement by doing that. We would have very much liked to get that 50-watt laser system for the Gemini Observatory. Around that time, we were looking for a laser source to do multi-conjugate adaptive optics at the Gemini South Telescope, which requires 5 laser guide stars. Unfortunately, it was impossible to do the technology transfer towards an international observatory like Gemini, so we had to start from scratch again, and we partnered with the Keck Observatory, the Center for Adaptive Optics, and the US Air Force to develop a new class of sodium guide star lasers, which resulted in contracts with Lockheed Martin Coherent Technologies, and they developed 3 systems, a 14-watt system for Gemini North, 20-watt system for the Keck 1 telescope, and a 50-watt system for Gemini South. And you can see on this slide a picture of the laser guide star constellation that has been created with that laser for multi-conjugate adaptive optics science observations that have been ongoing since 2011 at Gemini South in Chile. So another laser technology of interest, obviously, was fiber lasers, and there's been a number of approaches considered. The Lawrence Livermore National Lab has been looking at a some frequency type laser, fiber laser. Meanwhile, electro-optic systems, space systems in Australia has also been looking at a different type of some frequency laser using fibers. But the most successful approach to date has been the one followed by the European Southern Observatory. They identified Raman fiber laser technology as the best choice to produce continuous wave single frequency lasers, sodium lasers. Using fiber at 1120 nanometers, Raman shifted to 1178 nanometers, which is then doubled to create the 589 sodium light. So they went ahead and developed a prototype, a really good prototype of that laser, which has been installed at the Very Large Telescope in Chile to replace the initial continuous wave dye laser. It's called Parla. And they've transferred their technology towards their industry partners, Toptica, which is a laser company in Germany, and their partner, MPB Communications in Canada. And those companies have created a product which is nowadays the only commercially available laser system that you can buy. So the first units went to ESO in Chile to be installed on the Very Large Telescope there this year. They're going through commissioning. And the 5th unit went to the Keck Observatory and is also being installed on the telescope this year. A number of observatories are considering upgrading their systems with a Toptica laser. The problem that happened with some frequency continuous wave mod-log technology is that at the time these were developed, we didn't know that that laser format, that particular laser format, wasn't going to be very good to excite sodium atoms. There's actually a factor of about 3 less photon return from that system compared to a continuous wave single frequency system. So Gemini South, for instance, is looking at the possibility to replace their 50-watt some frequency laser with a Toptica 20-watt Toptica laser. The Subaru telescope is thinking about the same thing, and we're also considering that possibility for the US laser tracking station near Canberra in Australia. Future facilities that are in the design phase right now for extremely large telescopes, like the giant Magellan telescope, the European Extremely Large Telescope, and the 30-meter telescope, are also planning multi-laser guide star systems. GMT will have 6 laser guide stars. The European ELT will have 6 to 8 of them, and TMT will have 6 to 9 of them. And the first two are thinking of using Toptica lasers because that just makes sense. The TMT project is the only project that is departing from the idea and considering using micro-pulse some frequency lasers, which are being developed by their Chinese partners. So why should we think about developing yet another laser technology? Well, the Toptica sodium star laser is a beautiful machine. The problem is it's still quite expensive to buy, and many small observatories and SSA projects can't really afford a laser that is over $1 million. So there's also the sole source supplier risk. Right now, it's the only commercially available laser, and if suddenly Toptica decided to stop producing that laser for whatever reason, we'd be back to square one and have to develop yet our own sodium laser systems. It also happens that semiconductor laser technologies has matured quite a bit over the past decade, and some successful demonstrations have been done in the lab to show that this is a good technology to do sodium guide star. So the interest of that technology is, of course, that it's going to be really simple to create sodium light. It only requires the the number of components that you see on this chart. So this is the chip, the semiconductor chip creating the 1178 nanometer radiation. It's pumped by diode lasers brought to the gain medium by fibers. And then there's a turn mirror and a second harmonic generation branch with a nonlinear crystal to create the 589 nanometer light that exits through that mirror, and just a couple of elements to control the single frequency emission. This is the size of the laser head corresponding to this. So RIT Associates in Colorado has been demonstrating 589 nanometer optically pumped semiconductor lasers using a SBIR program funded by the NSF. This is the demonstrator here, which produced 3 watts single frequency with really good beam quality, the kind of wavelength, line width we want, a few megahertz, and demonstrating that it could effectively tune to the sodium D2A and the sodium D2B line. Later on their own funds, they demonstrated that they could go up to the 20 watt power level, albeit in a multimode fashion. So what needs to be demonstrated next is doing 20 watt with a single frequency laser. I might add at this point that it's possible to do D2B repumping with this technology as well, because either you just build a D2A laser and a D2B laser and you just combine the beams, or you could use an electro-optical modulator to create a sideband and create the D2B line this way. You can also think of going to much higher powers than the 20 watt level by using multi-chip configuration, and this has been demonstrated in the visible at other wavelengths, typically in the green. And you can also consider pulse formats if it appears that those are preferable to CW single frequency in the future to enhance sodium return. So RIT Associates and the Austrian National University have partnered to propose to develop a full-scale prototype of a semiconductor laser for gate star applications for astronomy and for space situational awareness. We've submitted a proposal to the National Science Foundation ITI program, which unfortunately was unsuccessful. And we've also submitted a proposal to the Australian Research Council for LEAF program, Linkage Infrastructure Equipment and Facility. And we've partnered with a number of academic institutions and other industry partners, including US Space Systems and Lockheed Martin. And the results of that proposal are pending. We will know whether we get funding in about a month from now. So should this proposal get funded, should we be successful in developing the prototype, we would have an alternative option to the Toptica sodium laser. So our goal is to demonstrate the same performance level or better in a system that has much lower complexity, and as a result of that, it's more efficient. It's going to be more affordable because it's just less components overall, and it will be in a significantly smaller package. So you may remember the title of my talk, which was From Dye Laser Factory to Semiconductor Laser. This is what, in 2001, a sodium guide star looked like. At the Keck Observatory, you had a full room of equipment. Here, at the base of the dome, housing, this is the room here with people in it. It's a container. The pump lasers, the sodium oscillator, and then you had to bring all that light up to the telescope, where there's another room here, and a big bench to do the amplification. So the liquid dye was also routed through the elevation cable wrap and azimuth cable wrap to be brought to this bench before the full power of the sodium gas star could be generated. So a fairly big laser. And we want to do this instead. We want to have just a tiny little box and put it behind the secondary mirror of the telescope. Thank you for your attention.
Thank you very much. Are there any questions for Celine?
Yes, Rich Holmes. Hi, Celine. Good talk. What limits the per-chip laser power on this latest generation of lasers?
Typically, you have to do a really good job at thermal management, and this is where the research and development work has to go in before you can increase the power level.
Thank you.
Okay, anything else? Yes.
How easy is it to wavelength tune that thing so the sodium's always fluorescing? You know, they always drift and you have to tune the wavelength slightly, especially if you got temperature fluctuations, you know, in your operating room. Things always get out of tune.
I'm sorry, I didn't quite understand the question.
How easy is it to wavelength tune onto your fluorescence line? Is it fairly...
With the semiconductor laser?
Yeah, with that
Well,
one.
the medium, the gain medium, is grown to be, emitting mostly around that line width to start with, and then you use temperature control on the birefringent filter, I believe, and on the ethylene, and then you use piezo on the one of the mirrors of the cavity to adjust the length of the cavity and tune to the frequency you want, and lock on the sodium D2 line on the peak.
Okay, thank you very much.
Thank you.
Okay, our next talk will be given by Francis Bennett. Dr. Bennett received his PhD in 2011 from the Australian National University, and since then he has been working as an adaptive optics scientist and optical physicist at RSAA. The title of his talk will be Adaptive Optics for Satellite Imaging and Space Debris Ranging.
Thank you. So I'm Dr. Francis Bennett from the Research School of Astronomy and Astrophysics with the Australian National University at the Mount Stromlo Observatory. For those of you unfamiliar with the Mount Stromlo Observatory, it used to be an astronomical observatory located in Canberra, Australia, until all the astronomical telescopes and optical manufacturing facilities were destroyed in a large bushfire in January 2003. This actually gave us an opportunity to rebuild and refocus our instrumentation program, and that allowed us to grow and include adaptive optics in our instrumentation work. So at the moment, we currently have the Advanced Instrumentation and Technology Centre, which is where we do our instrumentation work. So we have a growing team of AO experts, such as Francois Rigaud and Celine, who just gave the excellent previous talk. We have developed the preliminary design for the laser tomography adaptive optics system for the Giant Magellan Telescope. We are currently designing and will shortly be building an upgrade to the Gemini South Natural Guide Star tip tilt sensor. And we're also currently lab testing an AO system which we built for satellite imaging for the Korean Astronomical and Space Institute. So ANU is a partner of the Space Environment Research Centre, the CERC, who you may have heard about in James's talk earlier today. At RSAA, we're developing adaptive optics in terms of this research centre in space debris tracking, satellite imaging, and orbit perturbation. So the Mount Stromlo is home to the EOS Electro-Optic Systems Space Systems laser ranging facility. They have a 1 metre satellite laser ranging telescope and a 1.8 metre telescope with a higher power laser for debris ranging. Debris objects are quite a bit smaller than active satellites. They usually don't have retroreflectors, so you need the higher power to range those. So the RSA is collaborating with EOS to develop an AO-enhanced debris ranging system. So why do you need AO? Well, okay, my images aren't as nice as the videos we had before, but this is what you get if you look at an unresolved point source such as a star or a small satellite with a telescope around the 2 metre mark. The light's quite spread out, And the image will actually dance all over the place and it moves. That means that if you try to do any long exposures, the light just gets spread out further. So adaptive optics provides a near diffraction limited image, so you can end up with a smaller laser spot on the actual sky. So you take all the light from the star that's spread out here and you can concentrate it in just a couple of pixels. This increases the flux, if you're propagating a laser through the AO system, this increases the flux on the target, so you get a higher return signal. This will increase your sensitivity, so you can track smaller objects, you can track objects to a larger range. The image is also stabilized on the detector, which means you have a smaller full width half maximum, so you can have longer exposures if you need that. So if you look at a cross-section of the flux as it's spread out, if this is a laser beam propagated onto the sky at, say, 800 kilometers, you'll end up with light spread out over about a 20-meter area. If you use AO to correct your laser beam propagating onto the sky, you can actually end up with light concentrated to within about 2 meters. Not only is it more concentrated in terms of area, your peak intensity is much higher, so you can get sort of order of magnitude increase in your peak intensity. This is going to greatly improve your signal to noise because the number of returned photons is going to be drastically improved. If you integrate both of these curves over a small area, such as a small satellite or a piece of debris, then you actually, for the smaller the satellite, the larger the increase in returned photons, because all the intensity in a Gaussian's obviously in the peak. This is really good for ranging debris because most debris objects are really quite small and they're the ones that we don't know much about at this time. We can also use a higher power laser to track these uncooperative debris targets, and we use adaptive optics to correct the atmospheric turbulence and reduce the beam size on the sky. So this is a schematic of our AO system where we have a wavefront sensor, a Shack-Hartman wavefront sensor, which provides the turbulence information. We have a deformable mirror, which provides the adaptive optics correction for the laser beam. And we have an imaging camera, which keeps the laser pointed towards the target. So the laser beam joins the AO system with a dichroic mirror, reflects off the deformable mirror, and then on to the telescope and up to the sky. So the laser pulses themselves actually have to be aimed ahead of the target. So if you have a target here, and the black arrow is the optical axis of your telescope, you have to point ahead so that the laser pulses arrive at the same position where the target is at that altitude. Then, with the point-ahead angles are usually anywhere from 1 to maybe 10 arc seconds at most. And this is just because of the orbital velocity and the speed of light. After you get reflected or scattered photons from your target, by the time they return back to your telescope, the telescope has actually moved on in its track, so they appear off axis. With a laser guide star, you also have to point this ahead because you actually want to sample the atmosphere where the probe laser will propagate through, not where your telescope is looking. So you can also use adaptive optics enhanced laser ranging system with a more powerful laser to provide low thrust maneuvering. So if you can use the photon pressure, which is applied every time a photon reflects from a surface or is absorbed by a surface, need a high power ground-based laser with adaptive optics, you really need a lot of power, multiple kilowatts to do this. If you have a ground-based target here, a ground-based launch site and a target in orbit, and you propagate a laser towards that, some of the momentum will be projected onto the target's orbital velocity direction. And that means that you can either speed up or slow down the target so you can change its orbit. And this is really orbit perturbation. While it would be feasible to do deorbiting of some objects, at the moment it's really infeasible mainly due to costs. So we're currently developing a demonstration for this, a demonstration system for this. A successful demonstration will basically be if we can measure and perturb an orbit by a couple of 100 meters. There are some real challenges involved with this. We have to propagate an extremely high power laser onto the sky, so we need really good optical coatings, we need clean environments, things like that. We need a deformable mirror which can actually tolerate any heating effect, so even a small percentage of multiple kilowatts is a lot of heating. And we need really high precision tracking. So if we don't actually have the precision to measure the perturbation we've applied, then we can't actually say conclusively that we've done that. So what else can we do with adaptive optics? We can do satellite imaging. So AO is really widely deployed as an imaging system in astronomy. It provides near diffraction limited imaging for large aperture telescopes. So this is an image of an iridium satellite. So for example, if you want to resolve this with a ground-based telescope, you're going to need a relatively large telescope. You need sort of more than 1.5 meters to make it worthwhile. Anything smaller than that, and you're really only going to get 3 or 4 pixels over any sort of reasonable target in orbit. Anything larger than 4 meters, and it's going to be difficult to actually have it slew fast enough to track low Earth orbit objects. So if you want to get down to the Hubble region, around the 550 kilometers, it's moving really quite quickly. You need really good optics to do this, and you need adaptive optics so you can resolve objects better than the seeing. You can actually extend this principle to looking at geo-objects as well. We've seen this quite a bit over the last few days, but the way we're looking at doing it is using the high-precision astrometric catalogues, the Gaia catalogue, which will be coming out sometime in the next year or so. And if you use adaptive optics correction on the star and watch for the satellite as it passes close to the star, you can actually get really high precision, sort of down to the meter resolution for small objects from a single image. So I can give you an example of this with some simulated images of this iridium satellite. So under normal seeing conditions, I'm sorry I don't have movies like the other guy, but you might see something like this if you have a reasonably good seeing. With adaptive optics correction, you might be able to resolve something like this, where you can start to see features that are sort of a meter across as the reference scale. So this is the actual image scaled to the same pixel scale, just for reference, where that body is about a meter wide there. So you can start to resolve the solar panels, maybe some antenna, something like that. So how do we actually produce these images with our AO system? Well, we use modern high-speed, low-noise EMCCD cameras for this imaging, and we actually run them relatively quickly. So we capture multiple frames at a relatively high rate, even 60, maybe up to 150 hertz for a brighter target. We do that so we can actually stack multiple short exposures together to produce a final image with a high signal-to-noise ratio. So you can take multiple images like this, and instead of correcting the tip tilt with adaptive optics, you can just shift, derotate, and scale all the images, and then stack them together and end up with a final image, something like this. You can also apply image quality-based metrics, such as lucky imaging techniques, just to select the good images and then stack those. The main advantage of doing it this way is you remove a lot of complexity from your AO system. So you don't have to have any field derotators, you don't have to have high bandwidth, fast tip tilt mirrors with large stroke. You just ignore the tip tilt, you shift and add your images at the end. So the RSAA and EOS have been developing AO systems together for debris tracking. We're developing a demonstrator to use high-power laser to perturb the orbit of debris objects. And we're building compact and simple AO systems for satellite imaging. And we're really focusing on this compact idea by removing elements, making sure they're simple, and they're also high performance. Thank you.
Thank you. Are there any questions?
What's the seeing in Mount Stromlo? What arc seconds are not?
Craig probably knows better than I do, but maybe 1.8 on a good night. Okay. So down to 1 sometimes.
Thanks.
Okay, well, thank you very much.
Thank you.
Okay, well, our next speaker will be Rich Holmes. He's asked a couple questions, and he's very well experienced in the area. He's been working out on the island for quite some time, and right now he's serving as chief scientist of the Boeing operation here. His talk will be entitled A Comprehensive Comparison of Combat Data to Wave Optic Simulations.
Thanks, Glenn.
Yeah, thanks, Glenn.
Let's see. Great. So I'd like to first thank my co-authors, Rao Gudametla, who's the principal investigator for the AFOSR contract, Jake Lucas, and Jeremy Bose, who's currently an assistant professor at Michigan Tech. So what's combat data and why do wave optic simulations? So I want to answer those questions in this talk. And so let's see. So just first like to start out with an acknowledgement for that this work was funded under a laboratory research initiative by AFOSR, and the views expressed herein are not those of the DoD. So combat was a very long path experiment going from Mauna Loa to Haleakala, so 149 kilometers, and it was intended to improve our understanding of propagation of light through deep, strong turbulence. Based on our estimates, the scintillation index, usually much less than 1 for uplooking geometries, was over 100 in many of these experiments. So it was well into the deep turbulence regime. The data was gathered in February 2010. Laser light was projected from Mauna Loa to the EOS telescope over that long path at 3 wavelengths, 532 nanometers, 1064, and 1550 nanometers. The transmit apertures were about 27 millimeters, small, so they should, kind of like point sources. So it's a spherical wave geometry from an optics perspective. The received light was captured in the pupil plane, or imaged from the pupil plane of the telescope onto detectors. Each subaperture was 90. Each of the 3 subapertures was 90 centimeters in diameter, and the pixel sizes mapped to the pupil are about 3.5 millimeters. Also, the frame rate was about 200 hertz for all 3 wavelengths. So, although the experiment was intended to improve our understanding, it really created a lot of confusion. In fact, it produced a number of mysteries, and I think there have been a number of small teams trying to understand what's going on with the data, because it really didn't obey any of these standard theories of turbulence. So I'd like to discuss what those mysteries were and how wave optics simulations helped us resolve those mysteries. So first, again, we're going to start with trying to look at the data, understand what's going on, and then start getting a more quantitative understanding using wave optics simulation, varying the input parameters. So let's move on to the next slide. So here's some exemplary data, and this data, on your left is the 532 nanometer data, low, medium, and high scintillation cases for that wavelength. In the middle column is the 1064 nanometer data, and that's low, middle, high turbulence, or scintillation again. And then on your right is the 1550 nanometer data, low, medium, high. Each of those is labeled by NIV. NIV means normalized intensity variance. And you can see there's, that's a measure of the strength of turbulence. And so I just comment that the weak turbulence theories for these paths predicts up 100. And you don't see what any NIVs equal to 100 on that page. So something doesn't make sense for those weak turbulence theories. So there turns out we understand some strong turbulence theories, but they didn't explain the data very well either, and I'll go into that a little bit more later. So the other key mystery that you'll note in this data, this aspect of the data, is there's lots of little speckles. They're all about 1 to 3 centimeters in size, and what we expect from most theories is that the structure should be about 30 centimeters in size, about a third of those apertures sizes. So we see a little bit of that, but not very much. So I guess, so that's a mystery too, scale size here. And and also on top of all that, we did have a few camera artifacts, not many. You'll notice there's some saturation in the lower right there. So anyway, next frame. So a couple mysteries in the raw data, the spatial profile. Also in the temporal data, there was a mystery. So we saw very large variations in the total signal per subaperture, total signal in each aperture. So we're looking at three different wavelengths, again, left to right, 532 on the left, 1550 on the right. You can see that each of those is labeled with a standard deviation of the total signal, sigma ts, and it's on the order of 1, almost 2 in some cases. And that's much worse than would be expected from a scintillation analysis of the fades. So that was another mystery. That we expected, maybe 10-20% variation in the total signal. So we're going to probably provide some good explanations for that as well as we move forward on this. So on the next slide, so again, just to summarize, 3 unexpected properties of the data. One was the spatial scintillation strength, the normalized intensity variance, increased markedly, sharply with wavelength. And that's just the opposite of what you'd get from the standard weak turbulence theory. And in saturated turbulence, you might expect slow increase of the NIV with wavelength, but that wasn't what happened. That didn't happen either here. So strong turbulence theories didn't explain this either. Then their scale size, as I mentioned, it was much smaller than expected, and the temporal standard deviation was much larger too. So let's moving on to the next slide. So to address this, so the theories, the analytic theories, and even some of the semi-analytic theories, they didn't really work. So we tried something that was physics-based. We hope physics will explain our universe. So simulations, wave optics simulations, are physics-based. So we tried a physics-based wave optics simulation, and we looked at several different potential effects, and I'm listing them roughly in the order of importance. So we looked at alternative CN squared profiles. We looked at, so for these ground-to-ground paths, we expect stronger turbulence near the receiver and the transmitter, and we think that's in fact what happened, there's evidence for that, as you'll see in the following slides. Also, what about non-Kolmogorov turbulence? So there's no real reason to believe that turbulence should be anything other than Kolmogorov, except when it's not really in equilibrium. So we do have a reason to believe it was not in equilibrium in this case, because the path, the receive end of the path, is just upwind of a ridge of lava fields, and you'd expect those to produce a lot of turbulence, which probably hasn't equilibrated by the time that turbulence blows through the path. So that was, so we tried looking at that. We looked at turbulence inner and outer scale effects, including the hill bump. We looked at the relatively strong jitter sources near the transmitter to explain some of those fades. And one interesting effect was spatial averaging. It turned out you'd think 3.5 millimeters on a camera pixel would be small enough, but it turns out it probably wasn't based on these simulations. And so we'll go into that in a minute. And then we also looked at camera saturation. Turns out that wasn't a big effect, whether we included it or not in the analysis of the data or the simulation. It was on the order of a 5% effect. And then also anisotropy of turbulence. We just threw that in there. It's because it's something we can do, and it might be worth looking at. So next slide is, so just to talk briefly about the parameters of the wave optics simulation. We used roughly, it was a 149-kilometer path length, roughly 60 screens along the path. We did try 120, not much change. Then we also varied the grid size. We looked at 1024 by grids, 1024 by 1024, 2048 by 2048. We went to 2048 sometimes and made some difference, and if so, we used that result just to use the larger grids. And those larger grids were associated with finer grid point spacing. Our usual grid point spacing was about 1.2 millimeters, which was a third of a pixel size at the receiver. And the other parameters are pretty much in line with what you might, with what we've discussed. The other parameter we varied was the turbulence profile. The turbulence profile, we tried the standard Maui 3 profile. And that profile actually is shown in blue there, and counting for altitude and along the path. So you'll see results for that. And then we tried many different profiles, roughly on the order of a dozen, frankly. And we wound up with a profile that's a B in the end, which was basically 1 times the Huffnagle Valley 5-7 over Maui in Hawaii over land, and then a small fraction of Maui 3 over the ocean. So with those turbulence profiles, we can develop expectations of what the path should, propagation should look like. Assuming the first turbulence profile, A, the kind of the baseline Maui model, Maui 3, we wound up getting R naughts of 4 to 14 centimeters, not bad. And then we also got, doesn't sound too challenging, but you'll notice the isoplanatic patch angle there. It's fractions of a microradian. It's even nanoradians, tens of nanoradians. So that's definitely not your up-looking geometry. And then the spherical normalized intensity variance based on a weak turbulence calculation was 16 down to 5. All of those are strong turbulence. We don't expect weak turbulence, and we didn't see weak turbulence. It was pretty evident from the data. So let's see. So these calculations are qualitatively consistent with our expectations, but as you'll see in detail, we had to tweak the model significantly to obtain agreement with the observed data. So just like to summarize the results of many runs here. So we're comparing the top row, which is the data, the measured normalized intensity variance at the 3 different wavelengths. So 0.35 at 532 nanometers, 0.53 at 1064 nanometers, and at 1550 nanometers, it was about 1.2. So with that baseline scenario, that baseline simulation profile, the Maui model, you can see we were just way off. I mean, just ridiculous. So that was the source of confusion when people first started looking at the data. But then we tried other things. We went to that Maui 3 with a hill bump and then non-Kolmogorov, and that kind of helped. And then we tried bumping up the turbulence strength by a factor of 2, and that helped some too. But it turned out we would really have to bump up that Maui 3 model by quite a bit if we just use that. So we went to profile B, and that actually, I don't know if that helped or hurt, but then we used B with a hill bump and the non-Kolmogorov, and that actually did quite well. You can see here we've got about less than 10% disagreement here on the left, and on the right, we're right on, dead on at 1550 nanometers on average. Now, we didn't agree very well, though, however, at the 1064 nanometers, and I'm not sure. I think that may still remain a mystery for now, but that difference is significant, and I wouldn't call it great agreement. Let's put it that way. So in some of these cases, you can see we saw aliasing at our nominal grid spacing, so we went to finer scale, higher size, larger grids, and that did help, and it did improve the agreement somewhat in some cases. So the overall trend of increasing scintillation versus wavelength, you can see we did actually reproduce that here with the right choice of input parameters. And so let's see, what else? So, and that combined with the higher frequency non-Kolmogorov turbulence and the pixel averaging on the camera model. The camera modeling made a big difference. So the sim can explain the general trend of the NIV, which was one of the big mysteries. So if we go to the next slide, so let's look at spatial properties. So you saw earlier the data. We had very fine scale turbulence, and that's reflected in the spatial autocorrelation of the data. And so that's shown by that sharp central spike. It's only about a centimeter, even 7 millimeters in width, about 2 camera pixels. So that's definitely a clue that we might be averaging or smearing within pixels. So, and you'll also notice this dip. There's a dip that occurs out at about 40 centimeters, and that's roughly where the Fresnel zone of the standard turbulence theory says something should be. It should be a dip out there. So that was a little bit heartening to see some evidence of that. So we go to the next slide. We overlay that with the simulation data, and you can see with those same input parameters that we used before, you can see we get very good agreement at the central spike. We actually do reproduce that central spike as measured, and then we actually agree well further out. There is a region of disagreement here. I think if you looked at all the data, you'd see we did actually do a pretty good job of capturing that in other data sets, but here we're not. I'd say the agreement is only fair in that intermediate regime between 5 and 10 centimeters. So again, here we found that with the right input parameters, same input parameters as before, the simulation can provide agreement with the observed spatial scale sizes. So that provides an explanation for a couple of the mysteries we found in the data. So if we go to the next slide, we did see. We hardened by that success, we also decided to look at the temporal properties of the data. And so we did notice, so the total signal, by the way, is the sum of the analog and digital counts in all the pixels in the image, in the aperture, the 90 centimeter aperture. And we found ways to eliminate noise and saturation effects. So we did process the data very carefully, by the way. It's kind of an art. There's a number of papers published on how to do analysis of strong scintillation. And anyway, thanks. So anyway, the bottom line is we looked at the power spectrum. Now, if that power spectrum is shown as 2 up there, it's really, it falls off as f to the minus 2. If it were scintillation, it would fall off as f to the minus 3. And if it were a telescope jitter, it would fall off as f to the minus 4. So it turns out that the turbulence-induced jitter does fall off as f to the minus 2. So we hypothesize here, we provide an explanation that, at least consistent with the data, that the variations in total signal were likely caused by turbulence-induced jitter near the transmitter. So that's that. And I guess coming to conclusions, so simulation can provide, can explain the unexpected results in the NIV, the autocorrelation. Strong turbulence was required to close the transmitter and receiver in the simulation models to obtain that agreement. Non-Kolmogorov turbulence was also required, and pixel averaging. The simulation results for NIV at 1064 were still not a good match. There's still an issue there. Again, maybe that's that's the spatial properties. The temporal properties, I just mentioned that earlier. Looks like that's was due to strong atmospheric turbulence near the transmitter. So in summary, simulation can match the data for all 3 wavelengths, NIV, correlation, etc., using a combination of simulation effects in this case. And I think there's a lesson here. The bottom line lesson is that experiment and simulations indicate that imaging and data links at low elevation angles will not always perform as predicted by the standard theories, and or even by the limited current strong turbulence theory. You really want to try to use something like wave optic simulation to get a handle on it and to vary some of the parameters of that wave optic simulation. So anyway, I guess I have 5 seconds left, so thank you. So, yeah.
Great, thank you, Rich.
Yeah, thanks.
Are there any questions for Rich?
Well, thanks for the absence of questions.
Okay, good talk.
Thanks.
The next talk will be given by Roberto Benagaye, and Roberto's working at the Royal Academy of Sciences and Arts in Barcelona on designing and testing blind deconvolution algorithms with application to adaptive optics and non-adaptive optics images. And the title of his talk will be Anisoplanatic Imaging Through Turbulence Using Principal Component Analysis.
Okay, thank you very much. Let me understand first this machine. Yeah, okay. Okay, good. Okay, so I'm going to talk about the use of principal component analysis to correct the anisoplanatic effect in adaptive optics images. Atmospheric turbulence is probably the most important factor that degrades the quality of images. It can be partially corrected with adaptive optics, but only for a small angle that we call the isoplanatic angle. If the field of view is larger than the isoplanatic angle, there will be objects that are affected by, that are not well corrected by the adaptive optic system, and there will suffer from some, there will suffer from elongations or differences with respect to the guide star. If the stronger atmospheric layers are close to the pupil plane of the telescope, these distortions are not so severe. But if the atmospheric stronger turbulence are at higher altitudes, then this anisoplanetism effect is much more important. Even there are, for example, there is here a fainter star that is below the noise level because the adaptive optic system is not as effective as it should be. If we correct this image with an invariant PSF algorithm, then we obtain this, and we can see that we use as a reference star the guide star. We can see that the sources close to the guide star are relatively well corrected, but all the rest are suffers of aberrations and distortions. When we work with anisoplanetic data, we cannot consider the PSFs to be invariant anymore. It will vary across the field of view. We'll have a different PSF at each one of the locations. So the varying PSFs, the usual way to deal with this problem is to approximate the varying PSF as a weighting sum of a certain number of functions. That these functions can be considered invariant. In that case, the image formation equation can be approximated as with this summatory. So the object is weighted by the set of coefficients associated with each one of the functions, and then they are convolved with all of them, and the result is added up in order to create the image. We can choose there are many possibilities to choose the functions, for example, wavelets, shapelets, or principal components. Let's imagine we have a certain data set that can be described with two characteristics, axis Y and axis X. Principal components will create two new characteristics. The first one will be aligned with the maximum variability, the maximum variation in the data. And the second one will also be aligned along the maximum variation of the data, but with the restriction to be orthogonal to the previous one. Principal component has an interesting property, is that the maximum variation of the data and the minimum error reconstruction are reached at the same time. This is interesting because it means that with a minimum number of functions, we can recover the maximum amount of information, the maximum amount of possible information. Or in other words, if we want to recover the same amount of information with a different functions, we should use more number of these functions. How can we build our principal components from a data set of PSFs? Let's imagine we have a field of view of 256 by 256, just to put some numbers. Let's imagine that we have access to all the PSFs at each one of the locations, that the PSF support is 64 by 64. Then we have to arrange all our PSFs in a matrix, dataset matrix that we will call K, with as many columns as PSFs and as many rows as PSF elements there are in the PSF support. Then this principal component analysis can be computed by means of singular value decomposition of this matrix K. So we will obtain three matrices, U, lambda, and V, U with the functions we are looking for, with our principal components, with eigen PSFs. Lambda will have the eigenvalues, and V will have the coefficients that are weighting the field of view. Since matrix K is extremely huge, we also can work with the covariance matrix of K in order to reduce the dimension of the problem, since the useful eigenvectors of these two matrices are the same. All of them are contained in the columns of matrix U. And the coefficients, once we have computed matrix U from the covariance matrix of K, can be obtained just multiplying the transpose of U by K in order to obtain the matrix V. So here we have some examples of eigen PSFs. We can see that these two seems to be related with the symmetry of the PSFs, and these other two are more related with the diagonal and horizontal vertical elongations. here we have the set of coefficient fields associated with each one of the eigen PSFs. The coefficient field will have the same size as the field of view, 256 by 256. Because I have assumed that I have the access to all the PSFs in the field of view, then I can compute all the coefficients, all the fields of coefficients. If I have lost PSFs, then I will have also lost points in these fields. And these points should be computed in some way by interpolation or estimating them during the reconstruction process. Okay, so with a PSF support of 64 by 64, I can compute as much as around 4,000 eigen PSFs. If I don't want to use all of them, and I want to reduce the dimension of the problem, which of them are the most important? Which of them are the most characteristic of the data? Each of the eigen PSFs, each of the principal components, are associated with a certain eigenvalue. The larger is this eigenvalue, the more information is contained in the eigen PSF. So for the 4 principal components I showed you before, these 4 account for more than 95% of the information contained in the data. And if I use 10 principal components, I can recover more than 99% of the information of the variability in the field of view. For example, here we have 4 PSFs and the reconstruction using only 10 principal components. We can see that the similarity is pretty good. These are the differences between the previous images. They are 2 orders of magnitude lower, and they are precisely related with those principal components I started to reject in the reconstruction. Okay, introduction of principal components into the typical algorithms like Richardson-Lucy is relatively straightforward. We only have to substitute the convolution operator by the weighted sum of eigenfunctions. So the current estimate of the object at the current iteration is weighted by the coefficient and then convolved by each one of the eigen PSFs. Compared with the image and convolved back with the transpose of the eigen PSFs. Both the principal component and their transposes are using the same set of coefficients because both of them are associated to the same pixel in the field of view. Well, the previous equation was for assuming the likelihood is Poissonian. We also can extend this, assuming the likelihood is Gaussian. And we can build this iterative algorithm using Lamb-Weber iterations. We have applied these algorithms to simulations for the 3.5-meter SOR telescope for a field of view of 7.5 arcseconds with a bad sync of 1.2 arcseconds. The number in this table describing the turbulence in the atmosphere at different layers are real numbers. They were obtained from experimental campaigns for ELT telescope. The difference between the atmosphere 1 and atmosphere 2 is that the stronger part of the turbulence in atmosphere 2 is closer to the pupil plane, while for atmosphere 2 the stronger part of the turbulence are in higher altitudes. So the anisoplanatism for atmosphere 2 is much more important. The variability of the PSF is more evident, and the results I'm going to show you next are related to atmosphere 2. For example, this stellar field with stars with a magnitude up to 15, I think. If we use only 2 principal components in the deconvolution, we can see that we are not able to correct the distortions in the elongation direction or in the horizontal one. If we include the principal components associated to the diagonal elongation, then we are able to correct this, for example here, but not the horizontal one. And if we include this horizontal vertical term, then we are able to correct this problem. We also, this kind of algorithms suffer of noise amplification as the number of iterations increases. So we wanted to check if the number of iterations and the number of components are somehow related. So we designed this simulation, these stars in two coaxial circles. All the stars are the same, have the same magnitude. The guided star is placed in the upper right corner, so this part of here is more anisoplanatic. And we executed the Richardson-Lucy algorithm for a sufficient number of iterations. We can see that with 5 principal components, the reconstruction suffers of artifacts, distortions. With 10 principal components, stars in the inner circle are better reconstructed, but not in the outer circle. And we have to use 30 principal components to obtain a relatively well reconstruction. This is expected since the more anisoplanatic, the wider is the PSF, the more iteration, the signal-to-noise ratio is worse. You need more iterations to better focus the light into one single point. So if you want to protect your reconstruction from noise amplification, then you want to put as much information as possible. This is examples with extended objects. This is the ground truth image. This is simulated data. These are 2 reconstructions using PSF, invariant PSF. This one using the guided star here. We can see that there is almost no difference between the reconstruction and the original and the blur data. This one is using the PSF in the middle of the field of view. The reconstruction is better, but here there are still, the details are saturated, and the reconstruction at the bottom of the satellite is not very good. Using principal components, taking into account the variability of the PSF across the field of view, we can obtain a much better reconstruction. However, we can see that the reconstruction here of the satellite is sharper than here, which is still smoother. So if we increase the number of iterations in order to increase the sharpness of this part of the satellite, we could obtain the following: the same ground truth, simulated images, previous result, and more iterations. Then we can obtain a sharpener reconstruction, but the satellite here in this section start to suffer of noise amplification. So, it's clear that this kind of algorithms, even with principal components, they need some kind of regularization, some kind of prior information in order to homogenize the reconstruction level, no matter which position of the field of view we are. So we tried this other algorithm by Mirot and Portilla. This is the expression of this algorithm for invariant PSF. This is an inverse regularized filter where the object is at the current iteration is filtered in the wavelet domain. There is a regularization parameter. The authors, in order to compute this expression for principal components, decided to decouple the problem in two parts. The first one related with the PSFs, so they decompose the PSFs in principal components. And once you have chosen the regularization parameter, you can compute for each one of the PSFs, you can compute the inverse filters. So you have 2 data sets, one for the PSF, another one for the inverse filters, and they can compute principal component analysis for the PSFs and for the inverse filters. This is applied to the transpose of the PSFs, and this is applied to the rest of the equation. If you can assume that the filters and the PSFs change smoothly across the field of view, then this is a well approximation. However, the results we obtained were this. We obtained sharper reconstruction for higher number of the regularization parameter. For mu's larger than 9, our reconstruction started to suffer from artifacts because this expression is using a L0 norm as a prior information for the object, and this is probably not the best in prior information for this kind of objects. I wanted to show these reconstructions are not better than the ones I showed you before, but I wanted to show in order to see that inclusion of principal components in the deconvolution algorithms using a prior information is essential, and it must be done in a rigorous way. And just to finish, so we want to go on this research, just doing more, working in more realistic situations where you don't have access to all the PSFs. You have to estimate the coefficients, and you also have to develop, you want to develop also a blind and myopic deconvolution algorithm. Thank you very much.
Are there any? Yes, there are questions for Roberto.
So the question I have is related to computational cost. So I suppose you use fewer principal components because it's less expensive than if I use too many, right? If I use too many, then I have a more accurate approximation of my PSF.
I didn't want to check how many components are the most efficient because principal component depends on the data. So if I do this analysis for a certain kind of data, it's just for this kind of data. So I thought it was not very useful. It's just the more principal components you want to use, the better.
The better, right. So I was just wondering, so if you get it wrong, of course, you showed that the point spread function, I mean, so you don't get as good of, if you don't use this many, your reconstructions aren't as good. But could you combine it with a blind deconvolution method as well?
It's what I want to do next. But of course, the problem is that these examples are unrealistic. I am assuming I have all the PSFs. With blind deconvolution, you only can get some of them, and then you have to estimate the PSFs. You have to apply the principal components to the whole image, I guess, and then you have to restart and obtain a different principal components. I mean, it's not going to be easy. Yeah, please.
At the end, you mentioned that you have to impose a regularization prior, and you have a strength associated with that, and you showed several values of that. Do you have an algorithm to find the optimum regularization strength?
No, I tried the values suggested by the authors of the paper. And many others.
Okay, any more questions? Okay, thank you, Roberto.
Thank you.
The next talk will be given by David Mazurkiewicz, and he's worked in the field of optical interferometry for some time, and at this point in time, he's employed by Seabrook Engineering, a small business specializing in consulting and small optical assemblies. The title of David's paper will be Fundamental Constraints on Imaging Geosynchronous Satellites. Okay, David.
Thank you, Glenn. You're running a little bit early. I can fix that for you. What we're interested in doing is imaging geosynchronous satellites, not with the couple meter resolution that you've seen so far, but with something more like 10 centimeters. That's hard. With a full aperture telescope, you're talking 150 meters, something like that, at visible wavelengths, longer if you go to infrared. And we don't have those right now. You can do something else, maybe a LiDAR or synthetic aperture radar, something like that. But there's no relative motion for a geosynchronous satellite relative to the ground, so that doesn't work particularly well. Interferometry seems to be the alternative. Both at visible wavelengths and at radio wavelengths, we have the resolution. We have the VLBI systems at long wavelengths. We have a bunch of interferometers at short wavelengths that have the resolution. But to get this kind of resolution, the dynamic range, the resolution divided by the field of view, you need to have a lot of measurements. You need to have a lot of different azimuths for your long baselines. And that's missing from both instruments at both wavelengths at this time, and that's going to certainly affect the design of one of these instruments. I'm talking about visible light interferometry. On the long baselines, the fringe amplitude becomes very low. The signal's noise drops off as the visibility squared. So on a long baseline, you have lower signal to noise, you need a larger aperture to get to the same signal to noise, or a longer integration time. With just one long baseline, you don't get that long integration time because you're limited by the atmosphere moving the fringe around. We solve that problem by observing the fringe at a longer wavelength where the effective resolution is lower. And on shorter baselines, you can build a long baseline out of several short baselines and tie them together. So then we end up primarily with a relationship between the diameter of the telescope and the number of telescopes that you need to get out to the long baselines. And that is probably the most important trade in trying to design a system like this. So I've done more or less end-to-end simulations of the full interferometer all the way from the target through forming the fringes, recording the data, and then the data processing to data products that you can compare what they should be. But using something like that to work out a design trade, like this aperture size to number of apertures, is pretty difficult. And then also when you're talking about a big simulation, you've got tens of thousands of lines of code, and you're going to have to take my word that it works, or we're going to have to spend a lot of effort trying to do some sort of a validation, and that's difficult. So my goal today is to take the hard part, this trade between the diameter size and number of telescopes, and convert it into a problem that is simple enough so that most of you in the audience can actually do it. And then then things get interesting, because you can come to me and say, I don't believe your numbers. And at that point, we begin discussing the points that are important, rather than trying to guess why we don't understand what's happening. So that's the plan. What I'm going to do is spend some time talking about assumptions, the assumptions that I used in doing this, and then talk about the problem we've just discussed. There's the phase tracking. It's determining the phase on one of the short baselines. And then there's a phase transfer program, error budget, where we convert the measured phase on a short baseline at a long wavelength to the phase on a long baseline at a short wavelength. And then I'll look at the results. The assumptions and the results really don't matter, because I'm more interested in the process. But we'll look at them to get a feeling for where we should be and to get this started off. I think I've said all of that. So my assumptions, they're all pretty standard. 11th magnitude object in the visibles, pretty bright. They get quite a bit brighter in the infrared, which helps performance. Throughput is, I have an AO system with okay Strel, a little bit aggressive. All the other throughput, I assume 33%, which I think I can justify. I'm not sure you can build it. So I also did a pessimistic version that's about 1/3 throughput to get a feeling for how the performance varies as a function of the throughput of the system. The atmosphere standard, 10 centimeters and 10 meter per second wind. And the final point is the fringe visibility. How does the fringe contrast vary with baseline length? I don't know that. We've never measured one of these things, so you don't know it either. The best I can do is that Lockheed Martin did a simulation for one of their satellites, and that data was presented at the DARPA Deep Space Imaging Workshop this spring. I'm going to take that data and just assume that it's God-given rather than Lockheed-given. Okay, these are my assumptions for the photometry. The only thing that matters on this is I've taken a 5 millisecond frame rate. That number doesn't matter. It's just I'm using a number of photons in 5 milliseconds. If you have 2.5 millisecond frame rates, the signal will always be √2 smaller per frame. and you'll have to convert what you have to 5 millisecond frame to look at my charts. And I'm assuming photon noise dominates. That seems to be true. Read noise isn't an issue anymore, at least it won't be an issue in the very near future when we get to these cell X arrays in the near infrared. The EM-CCDs have a host of problems, but they're more or less photon noise limited and visible if you operate them properly. So that's, and then thermal noise isn't a problem to get out to 2 microns, which we're not really worrying, beyond 2 microns, we're not really worrying about that. And then the sky brightness just doesn't seem an issue either. This is the visibility model. On the left, this is what was presented at the DARPA workshop. You've got the fringe contrast running from 1 down to 10 to the minus 3 here. These are a few, somewhat less than 1% on the long baselines. It's for 550 nanometer wavelength. I've changed wavelength by just multiplying by the ratio of wavelengths to get performance at other bands. And each curve in each, that's not good. Each curve in this is a different azimuth. On the right-hand side, I have the upper and lower envelopes of the curve on the left. If you can't reach the upper envelope, then nothing works. So what I did is I just use this lower envelope throughout. And I said you have to reach that in order to make it work. I mean, we can argue about what should be there. There are people who have looked at this problem in the past and said you can't do it. And they've all used a 10-meter type uniform disk for their model. Bus is 10 meters in size. That's not unreasonable. There's a real big difference between a 10-meter uniform disk and these models. And that's because a real satellite has a lot of structure. And the structure has lots of high frequencies, and high frequencies are the visibilities on the long baselines that you use for fringe tracking as well as making the image. So I'm hoping that lower envelope line is correct, but it certainly needs to be validated before we actually go off and build this instrument. Okay, fringe tracking part. There are 2 sources of noise. There's photon noise, which is pretty easy. That's the top equation here. For long integration times, the fringe moves. And that's bad. If the fringe moves enough, then you're limited by the fringe motion instead of the photon noise. I use, again, a standard structure function. Time variation is 10 to the minus 5, time to the 5/3. I keep pushing the wrong button. The T naught is simply R naught converted into time space with frozen flow. And there's not much else to say there. The high frequency phase variations from this type of a model underestimate performance because the aperture averages over a bunch of the phases, so you're reducing all the high frequencies. Here's an example of that. This is 2 apertures, a 1 centimeter aperture and a 1 meter aperture passed over the same phase screen. And you can see that the small aperture in red has a lot more high frequency structure than the large aperture. That doesn't matter if you process the data by just averaging over some amount of time to get your phase. You need to be a lot more clever if you're going to take advantage of the smoothness you get from the larger apertures. And I try to be clever by using by including the prior information in the fitting. What I do is I have a model for how the phase varies as a function of time that's parameterized, and then I fit the parameters to the data. My model I'm using in this analysis is a spline. So I put a node every n frames, and then I calculate the value of that spline for every frame and compare the predictions of the spline at that time to the data at that time. And then I adjust the delay at each node to get the difference, to determine the values. And I adjust that to minimize the difference between the data and the model. And that works remarkably well. Here's the same thing in practice. The black line on the top panel, this is delay versus time. The top line on the upper panel is the simulation from the phase screen. The green line, which overlaps it almost perfectly, is the spline, which is fit through the red dots. The bottom panel shows the residuals, and this is actually this shows the kind of performance you can get out of doing this. This assumes a 50 millisecond spacing between nodes, so I have effectively a 50 millisecond integration time, which is long even for a 2 micron wavelength observation. On the other hand, the residuals between the spline and the data are running here at 16 nanometers, which is more than good enough to do imaging at a 0.5 micron wavelength. So it's a very this type of approach is much more powerful than what most people have been doing. And this is what happens when you put these two effects together. The left-hand side here is the photo. The left-hand side. Okay, this is the difference between the data and reality, or the fit and reality, as a function of the node spacing. On the left-hand side, you get this drop-off with larger node spacing because you have fewer free parameters and therefore less. You're beating down the photon noise. And then on the right, you have the errors in the model. So we'll get that right. These lines here, this upper line is a Kolmogorov atmosphere for just an average of some length of time. When you remove some tip tilts, you get something like the blue line. And this large drop-off over here is the aperture averaging from the good aperture. So changing the aperture size pushes this stuff to the right. Changing the signal to noise goes up and down. So these run from a low signal to noise to a high signal to noise. And changing wavelength cancels out. Well, it doesn't quite cancel out, but signal to noise is measured in phase. So the wavelength comes in through that phase number. And then I can fit let's go back one page. I can look at each one of these curves for different signal to noise, find the minimum, and then I have the best I can do as a function of the signal to noise. And that produces plots like this one here, which I use as the input to the performance model. Okay, once you've done this for different wavelengths and different aperture sizes, you can do various cuts through the data, and we don't really need to look at any of those right now. But that gives us everything we need to do the rest of the problem. So now we switch to bootstrapping. In the performance model, there are two things to deal with. One is short baselines to long baselines, and that just adds as root n. It's important because if you have too much phase noise, the visibility amplitude is reduced. And when the visibility amplitude is reduced, then the integration time needed to reach a signal to noise, a particular signal to noise, is increased. And it increases as e to the minus sigma squared. So that puts a fairly tight constraint on how good the phases have to be. And then that 124 nanometers that I'm using here for e to the sigma squared of 6 gives us, has to be divided up between all the various terms. Going from small short baseline to a long baseline is just root n. If you do n minus 1, where n's number of telescopes, n minus 1 is number of baselines. If you have telescopes in a ring instead of in a straight line, then you gain a factor of 4, because the long baseline is only halfway around. You can get there two different ways. And then the wavelength part, the change in phase is simply a matter of changes in refractivity of the atmosphere. So that number is on the order of 1.01 from the near infrared into the visible. And hopefully it's that simple. In reality, there's a bunch of things that cause decorrelation in the phase. You have to take them into account. There's differential refraction in the atmosphere. You can read through these. You can add your own to the list. But you have to just allocate errors for those. We've done an attempt to allocate those errors here. What's important? These only come in once for each of the two telescopes on the ends of the chain. The measurement noise comes in as we add telescopes. The measurement noise allotted per baseline drops, so that becomes important. And this gives us a multiplier of 6 when I e to the sigma squared. And results. We get things like this for my optimistic throughput. We're talking about the diameter of telescopes, 1 meter for a few telescopes, dropping to something like 0.6 meters here. If you get out to 30 baseline, 30 telescopes, this drops to about 0.6. And if you use the poorer assumptions, the poorer throughputs, we're talking about 1.5 meters dropping down to, this is 1.3 here, and with 30 telescopes, you're talking about just less than 1 meter. And I think I'm done. And I saved you one. I took care of 1 minute of missing time.
Actually, that was negative, but that's okay. Are there any questions? Okay, David, thank you.
You're welcome.
Okay, well, we've made it to the last talk of the session, and that'll be given by Henrik Schmidt. And Dr. Schmidt is an astronomer at the Remote Sensing Division of Naval Research Laboratory, and he's been working in long baseline interferometry. And I'd like you to come up and give your talk. And the title is Multiple Baseline Detection of Geostationary Satellite with the Navy Precision Optical Interferometer.
Okay. Oops. This is the light. Yeah. Okay. Thanks for having me here this afternoon. Thanks for sticking here till the bitter end. I'm going to talk to you about the multiple detection of multiple baselines interferometry fringes on a geosat with the Navy Precision Optical Interferometer. This is a work that we did, that's the NRL group and the Naval Observatory Flagstaff Station group. You guys probably know, if not, now we're going to know. In 2009, we observed this satellite here, DTV-9S, with the NPOI, and it detected interferometric fringes, which are shown here. This is the case of now, what we detected now, and I'm going to get to this in more detail. There's a lot of introduction about the problem. I don't have to go into detail. Geosats are far away. They're small. Well, they're big, but they're small in angular size. So the largest dimension is from something like, for the largest dimension for something like 2 meters is about 10 milliseconds. For 50 meters, about 250 milliseconds. DARPA had the goal, the Galileo had the goal of imaging these things with a resolution of 10 centimeters. Then the latest RFI came up with a possible demonstrator with a resolution of 40 centimeters, which still means 2 milliarc seconds. Observations imaging with 2 milliarc seconds. For a single telescope, this means 40 to 60 meters. There's no such telescope on Earth, and it would be extremely expensive to build one. As Michael Hart and Gerard Van Bell showed us in single telescope images. This on the left here is a CAC 10-meter telescope image of GE 23. This dimension here is about close to 50 meters, and you can put a few resolution elements on this telescope. If you want to find more details about the telescope, you need to do interferometry. Here on the right is a Horizont satellite. This is a satellite, a Russian satellite that was observed with a 3.5 meter AMOS telescope, and you see a blob, that's it. I wouldn't put anything on this structure here. We need interferometry. The single telescopes have the sensitivity. We need to actually build up on resolution by using interferometry. Just to give you an idea, we saw this too, but just a brief discussion here of how it works. You have two telescopes observing a satellite. The light from the satellite hits this telescope first, and you have an extra delay in here that you have to compensate along the path of light of this telescope. Once you compensate for this extra delay plus all the atmospheric turbulence and all other instrumental effects and vibration and everything that you can think of, you create constructive interference, which is a little bit hard to see here, but this is an interferogram. And what you measure on this interferogram is two things. It's the visibility, which is basically the fringe contrast, is the contrast between the bright and the faint areas of the interferogram, which is given by this equation here. And you also measure the phase. The phase is how much this peak, the peak of the interferogram is away from a reference, from a point of reference. All these values, the fringe contrast and the phase, they depend on the baseline. The baseline is the distance between two telescopes, and they also depend on the wavelength of the observations and on the structure of the source. Another one. For this experiment in particular, we use the Navy precision optical interferometer. Here is an aerial view. It's basically two interferometers, one inside the other. We have four little stations here, four fixed stations, which are the interferometric stations, the astrometric stations. They are used to measure precise positions of stars, which is one of the major requirements for the Navy. And we also have another 30 imaging stations spread in 3 arms. Each arm is about 250 meters in length, and the biggest baseline from this guy here to this guy here is almost commissioned. It's 432 meters. We can have baselines that go from 8 meters right now. Let me just put a little more in here. Baselines that go from 8 meters, 8.8 meters, all the way to 98 meters. That's what we have available right now. We do observations in the visual. It's in the wavelength range of 550 to 850 nanometers. The observations are dispersed, so we disperse this light into 16 channels that we're going to see later, the results as a function of wavelength. The resolution that we can achieve with this kind of interferometer for the shortest baseline of about 9 meters is 20 milliarcseconds, which corresponds to 4 meters at geo. And with the longest baseline is about 1 milliarcsecond, which is 20 centimeters at geo. The problem is we don't have the sensitivity. Right now, the sensitivity of the NPY is 6.5 magnitudes in the visual. That's because we have to use an aperture which is about 12 centimeters in diameter, which corresponds to the coherence length of the atmosphere. So why observe geosats with this instrument? Well, first of all, is a proof of concept. Second of all, there's 2 times of the year, in around February, March, and then in October during the equinox, where you have specular reflection of the sun on the geosats. They glint, they go to something like first magnitude, and it's a short period of time. It happens for about 2 minutes to 20 minutes, and we are able to observe them. In 2008 and 2009, we observed DTV-9S with 3 stations. We only had 2 baselines, one of 16 meters and another one of 19 meters. These are the results. This is the fringe amplitude as a function of wavelength. This direction is a higher resolution. We were able to fit these amplitudes with a 2-component model. First is a 1.1 meter component. The other one is a 4 meter component. They had the more or less equivalent flux levels, but we don't know where they came from because we don't know the position of these things on the satellite. We don't know the relative separation of these positions. And since it was a single baseline, it could be a structure that is very diffuse, like the solar panels. We don't know if it was something small in the solar panel that was glinting or if it was the whole solar panel that was glinting. So the next thing we want to do is do multiple baselines. And we use the results from these observations to guide the future work. First of all, this is, if I go back here, this is what we observed in this baseline. These are the amplitudes. When you get the models that better represented those observations, you see that the visibility amplitudes go from 1. They sort of hit a knee here, which is what we observed, and they fall down. We want to observe down here, hopefully even out there. That's where the information about the structure is. But in order to get there, you need short baselines. Like Dave was mentioning, you need to observe with baselines where the amplitude of the interferogram is high, so we can actually tie several baselines together, and as a result, you get you phase them together, and you can get information about the longest baseline. So that allows you to actually go all the way to longer baselines. In order to do this, we took some time, but we finally got to commission 3 new stations in the center of the array. This is one of the astrometric stations of the array. You can mix the light from all the astrometric or imaging stations. We put 3 stations around there that have 2 of them give a baseline of about 9 and 10 meters relative to this one. And then this one here gives a baseline of 13 meters. So everything's fine. We had some bad luck last year, about a year ago in March. We went observing, all the problems are solved, except for the weather. We got 2 snowstorms, one on top of the other, foot of snow on the ground. Then the atmospheric conditions are awful, but we actually got data. And here I can show you the, the results we got for this baseline here. This is, the names of the stations is W4 and Astrometric Center. The separation here is 8.9 meters. And each one of these panels here shows the power spectrum of the data, of the satellite data on a different channel. When you expand one of these channels, you see a strong peak around a fringe frequency of 2. This frequency of 2 is due to the fact that we modulate the delay by 2 waves in order to separate, to be able to separate it, to be able to integrate multiple baselines on the same spectrograph. We do a bias correction, and we can see that we still have a very strong signal on this baseline, on this wavelength for this baseline, for this satellite. We only got something like 4 seconds of data, which is a pretty short integration. But when we got to observe, it was the end of the glinting season, and the satellites were not glinting as strong as they would have been a few days before. This is data on the second baseline we observed, sorry, on the second spectrograph that we observed. The previous spectrograph had only one baseline, had only, this baseline here. The second spectrograph, we integrated light from all the 3 stations, which gives us this short baseline here, which is repeated from before, and this slightly longer baseline. This is 8.9 meters, this is 9.8 meters. And if I blow up one of these panels, you'll see 2 peaks. This is the same as before. It matches the one on the previous spectrograph, and you see this other peak in here. And when you look at the setup for the observations, we had a k-value, a fringe frequency of 2 for the shortest baseline, a fringe frequency of 3 for the longer baseline. We should have been able to see something at a very short, at k of 1, which should have been this long baseline here. All the data was in the same spectrograph. We should have been able to see it, but the integration time, sorry, the amount of time we were able to track the fringes was pretty short, was about 5 seconds on 5 seconds on this baseline and less than 1 second on this baseline. Nevertheless, we managed to detect on more than one baseline, and the dimension that the amplitudes of the of the interference of the visibilities are consistent with a glinting region of about 4 meters. We also, as a result of these observations, were able to do a little bit of photometry. As I said, we spread the light into 16 channels, and the black light here, the black line here, is DTV-7S, the satellite that we observed. The green line is a calibration star. It's a G9 giant, which is a little bit redder than the sun. The sun is a V minus I magnitude of about 0.7. This star is 1.2. And the satellite, the glinting satellite, the glint is very red. It's a magnitude color of 1.9 magnitudes. It's consistent with other observations, previous observations of other satellites. Now, what's the next steps? First, we're going to be observing in 2 weeks. We're going to be observing again with one of these configurations here, either this 3 stations plus this one here, or this 3 stations here and this guy here. And we hope that this time we have better weather and that we can actually get closure phases. Once you get closure phases, you can start to put information, you can start to infer about the positions of the different components on, relative to each other, the glinting components. So you can have an idea of how big the glinting components are and how far away they are, their orientation in the sky. Besides this, we are thinking about future telescopes. The Naval Observatory has 1.8 meter telescopes, the CAC outriggers, that are going to be installed. And our group, Sergio Bressano, which you can see here under the primary mirror, he developed 1.4 meter carbon fiber telescopes with CMA. And we are going to have some of these telescopes to install in the array and eventually do observations of satellites, not only when they're glinting, but actually during what you'd call quiescent times, when during regular conditions. So we can actually start understanding what the visibilities of satellites look like. As Dave pointed out, we don't necessarily know what these things look like. Nobody have ever observed satellites interferometrically when they are not glinting. So, thank you.
Are there any questions for Heinrich?
Thank you.
Okay, well, I want to thank the authors for providing such interesting papers for the session. And I want to thank you all for coming. I think Paul Kervin has a few things to say about the end of the conference, so let's transition to Paul.
And by the way, let's give a round of applause, not just to Glenn, but all the rest of the session chairs, because they really bring the technical content together. It's about time to give away some prizes, right? But before we do that, I guess I would also like to give a round of applause to MEDB, primarily this lady, Sandy, and all of her crew, because they really are the ones who make the logistics of all this run smoothly. So even though it looks like it runs smoothly, there's little things going on, and it's her team that makes most of that transparent to all of you. So thanks a lot, Sandy.
Thank you, Paul. Well, this week truly is the reward for what amounts to about a year's worth of planning. We start planning tomorrow with our session chairs and other members of the leadership team for next year's conference. But really quickly, I wanted to give a great shout out to the AV team that I see that's been helping here in the ballroom all week, as well as the folks that are on our AMOS conference planning team. Tiffany is in the back, Tiffany Lambert, Leilani Hearn, Michelle Coco, who's been holding it down at our hospitality desk for you all. This has really been a labor of love, and we're happy to be able to contribute in the way that we are to your work all year.
Yeah.